Imagine standing at the edge of a vast chessboard where the pieces are not carved from wood or ivory, but from entire worlds. Now picture one of those pieces, a luminous fragment hurtling in from interstellar space, sliding not in a random scatter across the board, but along a line so straight, so deliberate, that it almost feels scripted. That is what makes 3I divided by Atlas different. From the moment astronomers traced its path against the backdrop of the stars, the unease began to spread not because it was on a collision course with Earth, but because it seemed to be following a course at all. Most comets wander in like vagabonds, wild inclinations, odd angles, tilting far above or below the ecliptic plane. They are the drifters of the cosmos, carrying the signature of chance encounters with distant suns or gravitational slingshots we can barely reconstruct. 3I divided by Atlas, however, arrived with a suspiciously disciplined alignment. Its orbital plane is tilted by barely 5 degrees relative to Earth's own. In cosmic terms, that's not a fluke, it's a whisper of intentionality. It is as if this object, this intruder from the gulfs beyond, decided to roll neatly onto the same highway as our planets. And that whisper triggers a scientist's most unsettling instinct: to stop calling it a coincidence and start asking why. What elevates the tension is not the speed many interstellar objects race in faster than our telescopes can track, but the choreography. 3I divided by Atlas doesn't look like a drunken traveler tumbling into the solar system's gravity well. It looks like a ship making port. The way it threads itself into the gravitational lanes, brushing close to Mars's orbit in early October 2025, then pivoting toward its closest approach to the Sun, by the end of that same month, reads less like an accident and more like an itinerary. We call these waypoints, not random checkpoints on a galactic road trip, but deliberate markers that allow navigation, measurement, and control. And here is the problem: nature doesn't usually leave us such clean waypoints. Technology does. That suspicion sharpens when you realize how close the approach comes to being photogenic. At no point does 3I divided by Atlas threaten to strike Earth. That's important to emphasize, but safe distance is not the same thing as random distance. Its track will graze within what astronomers call a cosmic handshake, near enough to let our instruments watch, but far enough to avoid immediate panic. If you were designing a plan, yes, a plan for reconnaissance, for observation, or simply for signaling your presence, this is how you would do it. Close enough to be seen, far enough to be safe, perfectly timed to fall within windows of human perception. Of course, the rational mind resists that conclusion. Science is built on skepticism, and every voice in the observatory will insist on caution. Orbital mechanics can produce strange alignments by sheer probability. Gravitational nudges from stars and molecular clouds may funnel wanderers onto convenient tracks, but even the cautious mind admits, when coincidences pile up, suspicion becomes a scientific obligation. Astronomers felt that same unease in 2017 with Oumuamua, the first interstellar object detected, whose cigar-shaped light curve and unexplained acceleration led to debates that have not ended. They felt it again with Borisov, the second, though its messy cometary profile fit more neatly into expectations. Now comes the third, 3I divided by Atlas, and suddenly the pattern hardens, not a fluke, but a series. Not a traveler, but perhaps a messenger. It is here that the scientist's emotional compass tilts, not toward fear, not toward awe, but toward vigilance. A kind of intellectual alertness that says, pay attention, because the universe may be teaching you something you don't yet want to hear. That vigilance does not abandon data, it clings to it. Every degree of inclination, every perihelion distance, every predicted encounter date is written down, checked, and cross-checked. The numbers are not just figures on a chart, they are the fingerprints of intent or the smudges of chance. And right now, those fingerprints are beginning to look suspiciously clean. The next months will put that suspicion to the test. October 3rd, 2025, Mars will stand close enough to share a sky with the interloper, its orbiters straining their sensors to catch a glimpse. By late October, as 3I divided by Atlas dives sunward, Earth-based telescopes will watch its coma flare against the solar wind. And then, as November deepens, the object will slip behind the sun, cloaked for weeks in blinding light, invisible to our instruments. It is a sequence that reads like chapters in a play, each act timed with unnerving precision. For those paying attention, it is the very definition of a plan. If the opening movements of 3I divided by Atlas feel like the prologue of a deliberate journey, The details of its orbital design sharpen that feeling into something harder to dismiss. Think of a spacecraft navigator plotting a mission profile. The first decision is always the plane of entry. Do you dive in steep, risking minimal observation time, or do you slide almost flush with the ecliptic, maximizing contact with the local system? 3. I divided by Atlas has chosen the latter. Its inclination is a mere 5 degrees off the solar system's highway. That is not just unusual. It is, by statistical measure, profoundly rare. Out of the countless comets catalogued in our skies, only a sliver conforms so closely to the ecliptic. For an interstellar visitor, unbound by the formation history of our system, the odds are slimmer still. Yet here it is, gliding almost shoulder to shoulder with the planets, like a guest slipping neatly into line at a parade. This is why astronomers bristle when asked if it is simply a chance. They know what randomness looks like. Erratic inclinations, eccentric perihelia, orbits that scream of violence and chaos. 3I divided by Atlas, in contrast, feels orderly. Its perihelion distance, just under 1 astronomical unit, places it near the very same scale we inhabit, a scale convenient for instruments built on Earth. Its trajectory crosses Mars's orbit at a date that happens to fall precisely when orbital assets, our robotic sentinels circling the red planet, can be aimed outward to watch. The skeptic calls it a coincidence. The cautious scientist, though, whispers a different word: alignment. Alignment is dangerous because it tempts us. Human beings are wired to detect patterns even where none exist. It is a survival mechanism honed over millennia. See a rustle in the tall grass, and you imagine a predator. 99 times it is the wind. Once, it is the lion, and that one time justifies 1,000 false alarms. Science knows this bias, warns against it, and trains us to demand evidence before inference. Yet here we are, confronted with an interstellar object whose every waypoint seems engineered to intersect with our ability to observe. And the question becomes inescapable. Are we watching the wind or the lion? The emotional undercurrent here is subtle but undeniable. It is not fear in the Hollywood sense, no looming catastrophe, no impact scenario that ends civilization. The danger is quieter, the possibility that we are being studied, that our solar system is not as anonymous in the galactic sea as we once assumed. That possibility forces the scientific mind into a posture of vigilance. The data must be collected with ruthless care. Every error in astrometry, every miscalibration of light curves, could tip the scales between calling this a natural drifter or admitting it behaves like a reconnaissance probe. The stakes are epistemic. It is not about survival, it is about truth. And truth, in this case, comes at us in a sequence of milestones. October 3rd marks the Mars flyby close, but not collisional. Then late October to early November, perihelion is near Earth's orbit. After that, the blackout behind the Sunday. Each stage is like a waypoint in a flight plan. Each stage offers both opportunity and risk. Opportunity to measure. Risk of misinterpretation. When something follows such a script, the scientific instinct is to sharpen every tool we have: photometry, spectroscopy, occultation timing, and radar echoes if possible. Not because we expect to uncover evidence of alien intent, but because if such intent were there, and we missed it, history would never forgive our negligence. That is the essence of scientific vigilance, balancing skepticism with preparedness. Most likely, 3I divided by Atlas will prove to be a natural comet with peculiar coincidences, but if there is even a sliver of chance that its itinerary is not random, then ignoring that sliver would be the greater error. For centuries, astronomers have catalogued the sky with a mixture of awe and caution. Now, in the autumn of 2025, they face a test of both. Can they stay disciplined enough to resist wild speculation, yet open enough to recognize a signal if one is there? The balance is fragile. And 3I divided by Atlas, with its unnervingly tidy path, is pressing hard against it. What unsettles scientists most is not the geometry alone, but the way 3I divided by Atlas seems to anticipate our very methods of observation. Nature does not plan for our telescopes. Comets do not time their appearances to coincide with spacecraft trajectories. And yet, the sequence here feels unnervingly convenient. A close pass to Mars just when orbiters are in position. A perihelion that lines up with Earth's observational capabilities. A blackout behind the Sun that cloaks its behavior during the most critical phase. These are the details that prick at the scientific conscience, because if you were tasked with designing a test, probing how advanced a civilization's instruments really are, this is exactly the kind of itinerary you would write. It is in this context that astronomers speak of waypoints. The word does not belong to nature, it belongs to navigation. Sailors on Earth chart waypoints across oceans, aviators across skies, and spacecraft across planetary systems. To apply it to a comet is to betray our unease, because waypoints imply choice. If 3I divided by Atlas was simply an icy wanderer, its path should feel messy, stochastic, and indifferent to our eyes. Instead, each milestone is neat, as if marked on a cosmic map. From a purely mechanical standpoint, of course, gravitational dynamics can explain the arc. The sun's mass bends trajectories, and chance alone can produce apparent order. But from an emotional standpoint where the scientist's intuition hums beneath the data, the unease remains. Too clean, too well-timed, too close to being a plan. And that word, plan, is the fault line. Science resists it. A plan requires agency, and agency requires intelligence. No one wants to leap across that abyss without overwhelming proof. Yet the duty of vigilance is not to declare intent, but to prepare for the possibility. This is why 3I divided by Atlas feels different from Oumuamua or Borisov. Those were anomalies, curiosities, sparks for debate. This, by contrast, is an unfolding sequence with future chapters we can actually witness. We are not merely looking back at odd data, we are watching, in real time, a script being performed on the stage of the solar system. That is a rare privilege and a heavy responsibility. For the audience beyond the scientific community, the story resonates because it reframes our place in the cosmos. Most people have grown used to the idea that comets are icy relics, the leftovers of planetary construction. They come, they shine, they vanish, harmless, unless their trajectories intersect Earth. But 3I divided by Atlas tells a more provocative story, that even in the randomness of interstellar traffic, there may be patterns that suggest watchfulness, maybe even intention. Whether that intention is real or projected by our own pattern-hungry minds, it forces us to confront a possibility that shakes the very comfort of cosmic anonymity. What if we are not merely observing the universe, but being observed in turn? The next acts will test that possibility. If 3I divided by Atlas behaves exactly as the physics of a natural comet predicts, the unease will subside, replaced by the familiar sigh of relief that science has once again tamed mystery. But if it does not, if its brightness surges oddly at Mars, if its trajectory deviates after the blackout, if its coma chemistry continues to defy models, then the whispers of a plan will grow louder, and the world will have to decide how far it is willing to follow the evidence. For now, all we can do is watch with the discipline of skeptics and the caution of those who know history is sometimes written in the margins of coincidence. 3I divided by Atlas has entered our solar system, not as a threat, but as a question. And questions have gravity of their own. They bend our attention, pull at our assumptions, and force us into orbits of doubt and wonder. That is why vigilance matters. Because in a universe where most comets are mere wanderers, the one that looks like it carries a plan demands more than curiosity, it demands responsibility. To observe, to measure, to doubt, and to prepare. Whether it is a trick of chance or a signal from beyond, 3I divided by Atlas has reminded us that the cosmos is not just a backdrop to our existence, it is an active stage. And we are not alone in the theatre. From the moment telescopes locked onto 3I divided by Atlas, there was something about its light that refused to behave like the light of a simple comet. Most comets brighten in predictable ways. Gas jets flare symmetrically, dust scatters sunlight evenly across their comae, and the glow around them looks like a hazy sphere. But Atlas had a lopsided face, as if one side of its body carried a hidden lantern. Imagine driving down a deserted highway at night and seeing not the glow of stars, but a beam cutting deliberately through the dark, a beam that doesn't belong there. That is what astronomers saw in the brightness profile, an asymmetry that begged for explanation. The temptation, of course, was to reach for metaphor. One headline whispered, "headlights," another called it a cosmic torch. But beneath the poetry was a puzzle. If 3I divided by Atlas is nothing more than ice and dust, then why does one hemisphere shine so much stronger than the other? Outgassing should spew in multiple directions as the surface warms unevenly, producing random flickers. Yet Atlas's asymmetry persisted, as if locked into a pattern. Some speculated that perhaps we were not seeing dust at all, but heat management, carbon dioxide venting preferentially from one region, shedding thermal load into space the way a radiator might. If so, the comet wasn't just glowing, it was cooling. This is where curiosity rises, because carbon dioxide is not the usual star of the show. In most comets, water vapor dominates the plume. Here, the balance tilts strangely towards CO2, a molecule more efficient at carrying heat away. The comet's spectrum suggested an overwhelming presence of it, creating an aura hundreds of thousands of kilometers across. That alone makes Atlas feel different. Its very chemistry amplifies the asymmetry, like a spotlight turned outward. Could this be a natural quirk, the fingerprint of an object formed in a CO2-rich nursery far beyond our system? Possibly. Could it also be a sign that we are watching deliberate thermal venting, a technology disguised as cometary breath? That possibility is harder to rule out than some would prefer. Still, vigilance demands restraint. Science has been burned before by the seduction of anomalies. Oumuamua's acceleration, unexplained at first, led to endless debates about solar sails and alien probes. Years later, the data remains ambiguous, and the controversy is a reminder. Extraordinary claims require extraordinary proof. With Atlas, the asymmetry in its glow is not proof of intent, but it is a clue, and clues demand to be followed. To ignore them would be to turn away from the very principle of curiosity that drives science forward. That is why this strange brightness matters. Whether it is a cosmic radiator or a fluke of volatile chemistry, it teaches us something profound about interstellar visitors. They are not all cut from the same cloth. Each carries a signature, a story written in light. And Atlas's story, at least in this chapter, is one of imbalance, an imbalance that looks suspiciously like a signal. If the asymmetry of 3I divided by Atlas were a single night's quirk, a momentary flare in the data, most astronomers would shrug and move on. Comets are temperamental. They spin, fracture, and burp gas in unpredictable bursts. But what makes Atlas's light so compelling is persistence. Night after night, week after week, the lopsided glow repeated itself, like a metronome refusing to lose rhythm. That kind of consistency doesn't just catch the eye, it nags at the mind. It is the difference between a spark of chance and the pulse of a pattern. And patterns demand explanations. The first camp of explanations leans on geology, or more precisely, on outgassing physics. A patch of CO2, too rich ice near the surface, could vent more vigorously than the rest, creating a plume angled like a headlight beam. Because carbon dioxide sublimates at lower temperatures than water, it can flare earlier, before the rest of the surface engages. That would naturally bias the comet's brightness, making one side disproportionately luminous. If Atlas is simply carrying a chemical fingerprint from its birth environment, then the asymmetry might be no more surprising than finding extra salt in a soup, peculiar but not profound. This explanation is comforting because it keeps the mystery inside the walls of known science. The second camp of explanations leans towards something harder to dismiss: a functional interpretation. If the CO2 jets are not random, but rather systematically placed, then they could act as radiators, shedding internal heat. Spacecraft engineers know this problem well. Electronics, fuels, and structural components cannot endure unchecked heat. Radiators vent excess energy into the vacuum, and if you were to disguise such a mechanism within a comet-like body, it might look eerily similar to what we are watching now, one hemisphere glowing as though a system is shedding its heat load in a controlled, directional way. Between these two camps lies the tension that defines modern scientific vigilance. Too much skepticism, and you risk ignoring an extraordinary discovery. Too much credulity, and you risk being fooled by coincidence. What makes 3I divided by Atlas so haunting is how it forces us into that balance. The comet is not doing anything overtly impossible. Every watt of its glow could, in theory, be explained by natural sublimation, and yet, the way it organizes that glow, the persistence, the directionality, the CO2 dominance keeps dragging our minds back to the question, what if? Curiosity thrives on such questions, but caution anchors them. If this is simply chemistry, then Atlas offers a unique laboratory for testing how comets evolve when born in alien nurseries, perhaps around stars very different from our own. Its CO2MAZ heavy signature may help us model what icy bodies look like beyond the solar system, giving us predictive tools for the thousands of exoplanetary systems now catalogued. That alone would make it historic. But if it is more than chemistry, if the asymmetry is engineered, or at least structured in a way that natural randomness cannot explain, then we are standing on the edge of a different kind of history. For the public, that is the tightrope between wonder and wariness. The allure of headlights in space makes for headlines, but the deeper value lies in how we handle that allure. We cannot leap blindly into speculation, but neither can we dismiss the clues outright. 3. I divided by Atlas has given us a phenomenon that looks suspiciously like a beam in the night. Whether that beam is natural or intentional, it demands our attention, because in either case, it expands the horizon of what interstellar visitors can teach us. The puzzle of 3I divided by Atlas's uneven light is not just about brightness, it is about what that brightness implies for the object's internal story. A comet's coma is its confession. The gases and dust spilling into space are direct whispers from its hidden core. For most comets, water dominates those whispers. For Atlas, the voice is different, carbon dioxide speaking louder than expected, carrying heat away with startling efficiency. And that difference matters, because if the comet's chemistry is truly that skewed, then either we have stumbled onto a rare breed of interstellar body, or we are looking at behavior designed to mimic one. Think of the way headlights cut across fog. To an observer, the light itself is obvious, but the reason behind its persistence tells you whether you are seeing a car on the highway or a trick of the mist. That is the tension with Atlas. If its headlight is nothing but a volatile patch venting at the right angle, then the mystery is solved, even if the solution is rare. But if the headlight holds because it is sustained, managed, and repeated with almost mechanical regularity, then we may be seeing a process that blurs the line between natural and engineered. That is why scientists refuse to stop watching. The risk of overreading is real, but the risk of underreading, of ignoring a signal wrapped in gas and light, is greater still. Curiosity drives us toward the extraordinary, but caution reminds us that nature often surprises with perfectly mundane tricks. Volatile chemistry, rotational quirks, and surface fractures can all conspire to paint illusions of design. That is why the next months of observation are so critical. As Atlas nears perihelion and then disappears into solar glare, the question will sharpen. Does its light curve remain faithful to the headlight asymmetry, or does it dissolve into randomness? If it holds steady, suspicion grows. If it fades, the anomaly may shrink back into the realm of natural variance. Either way, the data will matter far more than the metaphors. And that is the lesson here. Vigilance is not about jumping to conclusions. It is about holding tension, letting curiosity pull us forward, while letting caution slow our stride. Atlas forces us to practice that discipline in real time. Its glow is a challenge, not just to our instruments, but to our scientific humility. Do we have the patience to watch without overreacting? Do we have the courage to admit if the evidence suggests something more than geology? These questions will not be answered in headlines. They will be answered in the fine print of light curves, spectra, and orbital models. Yet even in that fine print, the larger story endures. 3I divided by Atlas reminds us that interstellar visitors are not just background actors. They are provocations, each carrying a different accent in the language of the cosmos. This one speaks in asymmetry and imbalance, in beams of carbon dioxide that cut across the void like phantom headlights. And whether those beams are nature's tricks or something more deliberate, they force us into the very posture that defines scientific progress. Curious enough to lean closer, cautious enough to resist being swept away. So when the glow of Atlas fades into the sun's glare, and the world waits for its reappearance, the unease will remain. Not because we fear catastrophe, but because we sense the weight of a question we cannot yet answer. Is the light we see a comet breathing, or a system cooling? Is it a coincidence, or communication? Until the data resolves that tension, all we can do is stand at the edge of the night, staring at that stubborn beam, and admit what few dare to say out loud. Sometimes the cosmos does not just illuminate, it interrogates. Imagine holding a ruler in your hand, not one marked in inches or centimeters, but one designed to measure the weight of coincidence. That is what science must invent when confronted with anomalies like 3I divided by Atlas. Numbers alone are slippery. They can be shaped into patterns, fitted into narratives, or dismissed as noise. What the scientific method requires is discipline, a framework that forces researchers to step back, quantify, and resist the seduction of strangeness. Without such discipline, every flicker of data becomes a revelation, and every comet becomes a conspiracy. With discipline, Anomalies are filtered, ranked, and examined with calm precision. The core idea is simple. Not all anomalies deserve the same level of attention. Some are statistical quirks, interesting, but harmless. Others resist natural explanation and demand closer scrutiny. To separate the trivial from the transformative, scientists need a scale, a kind of anomaly ruler. It is not about deciding in advance what is alien or artificial. It is about building a hierarchy of strangeness, so that our limited energy and resources focus on the signals that truly test our models of nature. Think about it in everyday terms. When a doctor sees a patient, they don't treat every symptom as equal. A mild cough gets a different score than chest pain. The same logic applies to anomalies in space. Oumuamua's unexplained acceleration was like chest pain, not immediately lethal, but a symptom that could not be ignored. Borisov, by contrast, looked like a messy but ordinary cold, an interstellar visitor, yes, but fitting into expectations. Atlas, however, is somewhere in between. Its disciplined orbital plane, its waypoint-like trajectory, its asymmetric glow, all are symptoms that, when stacked, begin to raise the score. And that stacking is the point. A disciplined anomaly scale forces scientists to treat data like bricks. One brick is not a wall, 2 bricks are still not a wall, but as you pile them together, shape emerges. Inclination just 5 degrees off the ecliptic, rare but not unheard of, score it modestly. Add in the asymmetric brightness, persistent over weeks, another brick, higher score. Add in the timing of encounters, Mars in early October 2025, perihelion late October, a blackout in November, just when observation becomes most critical, and suddenly the wall begins to rise. Each feature on its own is survivable. Together, they whisper that maybe we are not just seeing a coincidence, but the discipline here is not only in scoring, it is in restraint. To build the wall too quickly is to risk collapsing under weak bricks. Scientists know the dangers of rushing to judgment. History is full of anomalies later explained by mundane causes. In the 1960 seconds, pulsars were nicknamed LGM for little green men, until better data revealed them as neutron stars. Even Oumuamua, to this day, divides opinion between odd rock and possible technology. The lesson is clear. Anomalies tempt the imagination, but imagination is not proof. Only through careful, structured assessment can we know when the score has reached a threshold that justifies extraordinary claims. And this is where 3I divided by Atlas tests us. Its features are seductive because they line up like plot points in a script. The trajectory looks like a plan, the glow like a headlamp, the chemistry like thermal venting. But the scientific posture must remain calm, almost militarily disciplined. No panic, no premature declarations. Just a steady hand on the ruler, measuring each oddity in turn. If the scale says it's a 3 out of 10, treat it like a 3. If new data pushes it to a 7, adjust accordingly. The goal is not to suppress curiosity. The goal is to protect curiosity from running ahead of the evidence. This is the balance the public often misunderstands. To outsiders, caution can look like denial. To insiders, caution is the only way to preserve integrity. The curiosity that drives scientists to stare at Atlas night after night must be paired with the calm that prevents them from shouting signal at every irregularity. That pairing curiosity bridled by discipline is what makes science credible, and it is what makes this moment with Atlas so critical. So as October 2025 unfolds, and as Atlas hits its waypoints, scientists will keep score, not because they want to dampen excitement, but because excitement without measurement is chaos. The ruler of coincidence is not just a metaphor. It is the tool that allows us to transform wonder into knowledge and suspicion into testable hypotheses. Atlas may or may not be extraordinary, but our method for judging it must be. If the first principle of discipline is to build a ruler for coincidence, the second principle is to use it consistently. The danger with anomalies is not just misinterpreting them, it is cherry-picking. Human beings are natural storytellers, eager to weave patterns out of fragments. But science is not storytelling. Science is scorekeeping. Every anomaly must be tallied by the same criteria, whether it excites us or disappoints us. Without that consistency, the scale collapses into bias, and bias is the enemy of truth. Consider again how 3I divided by Atlas challenges this discipline. Its near-ecliptic orbit tempts us to see intention, Why here, of all planes? Its waypoint sequence Mars, then Sun, then Blackout, tempts us to see choreography. Its asymmetric brightness tempts us to see technology. Each of these anomalies tugs at the imagination, pulling us toward a narrative of design. But the scorekeeper must resist. Instead of saying, "This looks like a plan," the disciplined scientist says, "How unusual is this compared to the baseline?" If interstellar objects are expected to arrive at all sorts of inclinations, then a 5-degree tilt is rare but not unprecedented. Score it modestly. If comets often show asymmetric outgassing, then Atlas's headlight is notable but not unique. Score it moderately. And so on. The discipline lies in not letting excitement inflate the numbers. This scoring process may sound mechanical, even dull, but dullness is a feature, not a flaw. It is what keeps science from becoming spectacle. Imagine a courtroom where every piece of evidence was greeted with gasps and speculation. Justice would collapse. In the same way, the cosmic courtroom demands that we weigh anomalies with calm precision. That does not mean ignoring them. It means filing them properly. The anomaly scale is the filing cabinet of the universe, preventing us from drowning in sensationalism. Yet within this dullness lies a quiet power. Because once you have scored enough anomalies, patterns emerge. Not narratives imposed by imagination, but structures revealed by numbers. If Atlas scores high across multiple categories, trajectory, brightness, chemistry, then the cumulative score itself becomes an anomaly. That is when suspicion hardens into scientific obligation. A single oddity can be dismissed. A stack of them, each scored and verified, forces attention. The ruler does not scream, it whispers, but its whisper carries weight. The calm required here is not passive. It is active, almost athletic. It takes strength to resist the temptation to dramatize. It takes patience to wait for data through long nights, to recheck calibrations, to compare instruments across observatories. Scientists are not immune to excitement. They feel the pull as strongly as anyone. But discipline means channeling that excitement into process. The observer staring at Atlas through a telescope in October 2025 is not a dreamer. They are a scorekeeper. Every data point is a tick mark, every light curve a ledger entry. Over time, the ledger itself tells the story whether Atlas is ordinary or extraordinary. The public often wants shortcuts. They ask, is it alien? Is it natural? They want a headline, not a histogram. But the scientific answer, at least for now, must remain calm. We are building the score. We are watching the pattern. That answer frustrates. But it protects us from both premature celebration and premature dismissal. It holds us steady on the razor's edge between wonder and wisdom. And here lies the deeper lesson. Discipline is not about suppressing imagination, it is about sequencing it. Curiosity asks the question. Discipline structures the answer. Together, they form the balance that allows science to move forward without falling. In the case of Atlas, the balance is even more delicate, because the anomalies align so neatly that they almost beg for narrative. But the true measure of our progress will not be whether we told the most exciting story. It will be whether we built the most reliable score. So, as the weeks pass and Atlas continues its journey, the task is not to decide in haste, but to score in patience. The anomaly scale becomes our compass. It keeps us moving, step by step, brick by brick, toward clarity. And clarity, not sensation, is the true prize of vigilance. Discipline is not just a method, it is a mindset, a way of carrying oneself in the face of mystery. And nowhere is that more necessary than with 3i divided by Atlas. The final principle of an anomaly scale is not only to score but to decide when the score demands action. Numbers, after all, are only useful if they guide behavior. A doctor does not stop at diagnosing chest pain. They prepare the operating room if the risk is high enough. In the same way, scientists must decide at what point an anomaly crosses the threshold from curiosity to priority. For Atlas, that threshold may come soon. If its inclination, waypoint sequence, and asymmetric glow continue to hold as it approaches perihelion and slips into blackout, the cumulative score on the anomaly scale could climb beyond comfort. At that point, the duty of science is not to declare alien, but to intensify scrutiny. More telescopes, more cross-checks, more models. The response must be proportional to the score, not to the speculation. This is what separates science from sensationalism. The scale does not guarantee answers, but it guarantees discipline in the search for them. And this discipline carries a deeper emotional weight. It asks scientists to remain calm even when the data feels electric. It asks them to keep their voices measured, even when their hearts race with wonder. It asks them to trust the slow process of verification, even in a world that craves instant conclusions. This is why discipline, the rigorous, almost military sense of discipline, is not cold. It is protective. It shields truth from distortion, like a lens shielded from glare. Without it, the brilliance of anomalies blinds us. With it, we see clearly. Even if the view is unsettling, there is also a humility baked into this process. The anomaly scale does not promise certainty. It promises only structure. It admits that we are fallible, that we see patterns too quickly, that we leap to conclusions too eagerly. By forcing us to score instead of shout, it humbles us before the cosmos. And perhaps that humility is exactly what Atlas demands. Whether it is natural or not, Atlas confronts us with the possibility that the universe still has tricks we cannot anticipate. To approach those tricks with arrogance would be to fail. To approach them with discipline and calm is to honor the very spirit of inquiry. For the public, this framework offers more than reassurance. It offers participation. To hear that scientists are scoring anomalies is to realize that discovery is not a binary of yes or no, alien or natural. It is a continuum, a process. Every new comet, every new data point, shifts the score slightly, building toward a clearer picture. The public can watch not just the spectacle of a bright object in the sky, but the spectacle of science itself, patient, methodical, unglamorous, but profoundly human. In the end, the lesson of Atlas may not be about what it is, but about how we respond to what it could be. If it is ordinary, the scale will reveal that through low scores, and we will add it to the catalogue of interstellar wanderers. If it is extraordinary, the scale will build the case brick by brick until skepticism yields to evidence. Either way, the process protects us from error, from hysteria, from the arrogance of certainty. It keeps us steady in a universe that delights in shaking our assumptions. So, picture that ruler again, suspended in your hand, marking not inches, but improbabilities. Each observation of Atlas lays another notch upon it. Each anomaly is measured, not worshipped. Each suspicion is tempered by a score. And slowly, patiently, we build a portrait of truth. That portrait may show us a comet unlike any we have seen. It may even, one day, hint at technology hidden within ice. But whatever it shows, it will be earned not through leaps of faith, but through the quiet, relentless discipline of science. In this way, Atlas teaches us twice. First, through its anomalies, which challenge our models. Second, our response, which challenges our character. Will we remain calm when curiosity beckons us into chaos? Will we stay disciplined when imagination tempts us to run ahead? The anomaly scale is not just about Atlas, it is about us. And in that mirror, the measure of our science becomes the measure of ourselves. Picture yourself in a dark hall, lit only by a single chessboard under glass. On the board, one side plays itself. Every move lands with unsettling perfection, every piece sliding into position as though guided by invisible hands. Now imagine you are told this is a coincidence, that the pieces are simply falling into place by chance. How long could you watch before your skepticism outweighs your patience? How many flawless moves can you accept as random before logic begins to whisper, "This cannot all be accidental"? That is the dilemma 3 I divided by Atlas has set before us. In science, coincidence is not an enemy. We expect improbable alignments to emerge simply because the universe is vast and time is long. Toss a million dice, and rare sequences will appear. But what Atlas presents is not a single improbable roll. It is a cascade, a sequence of results that appear aligned, step after step, each one compounding the odds against randomness. Like watching a gambler roll sixes again and again while smiling across the table. The longer it continues, the harder it becomes to write it off as luck. Start with its approach. 3 I divided by Atlas slides into our solar system, not at some wild angle, but almost flush with the ecliptic, the very plane where our planets reside. For an interstellar object, unbound by our system's formation, that alignment is rare. Not impossible, but statistically small. A single brick in the wall of improbability. Then look at the timing. Its trajectory carries it across Mars's orbit in early October 2025. a moment when orbiters happen to be in a favorable position to observe. Again, not impossible. Planets and comets cross paths often, but the synchronicity raises eyebrows. Another brick. Next comes its perihelion, late October, conveniently near Earth's orbital distance. That places it squarely within the reach of our ground-based instruments, before vanishing behind the Sunday. Another brick. And finally, the blackout itself, a disappearance that occurs exactly when astronomers most want clarity, leaving us blind during the most critical interval. The wall grows taller still. Individually, each of these anomalies is survivable. Astronomers could shrug off a low inclination, a Mars crossing, a perihelion near 1 AU, or a solar blackout. Nature allows for such quirks, but probability is not judged in isolation. It compounds. The likelihood of all four aligning neatly is the product of their individual odds. To believe Atlas is pure coincidence is to believe in the improbable, not once, but 4 times in sequence. It is like flipping a coin and seeing heads appear 4 times in a row, while the coin happens to land in the very spotlight where the whole room is watching. Yes, statistics permit it, but logic recoils, and that recoil is not hysteria. It is controlled skepticism, the most disciplined form of doubt. Controlled skepticism demands that we pause, quantify, and resist both denial and fantasy. It asks us to keep a scorecard, multiplying odds instead of multiplying stories. In this framework, Atlas becomes more than a comet. It becomes a case study in compounding improbabilities. Scientists are not claiming intention. They are simply acknowledging that when coincidences pile high enough, vigilance becomes mandatory. The analogy of orbital chess captures this tension perfectly. Atlas does not stumble like a drunk wanderer across the solar board. It moves like a rook gliding along a file, like a bishop tracing a perfect diagonal. Mars encounter, Earth range perihelion, solar blackout. Each move lands on a square that matters to us, and with each move, suspicion grows that the pieces are not tumbling randomly but being placed with foresight. The skeptic's job is not to panic at this board, but to measure how improbable it is that chance alone could script such a sequence. For the scientist, this becomes an obsession. Charts are recalculated, simulations are rerun, probability distributions are drawn, revised, and tested again. The conclusion is never certain. Chance always remains a candidate, but the wall of improbability grows with each confirmation. And with that growth comes a creeping question. How many perfect moves does it take before logic itself bends? How many stacked coincidences transform randomness into choreography? This is the razor's edge where Atlas keeps us suspended. On one side lies coincidence, on the other lies intention. Neither can be declared without evidence, but the balance tilts with every anomaly logged. Controlled skepticism holds us steady, refusing to fall into hysteria. And yet, beneath that calm surface, logic hums with a quiet obsession, the recognition that we may be watching a pattern too precise to dismiss. The human mind struggles with compounded improbabilities. 1 coincidence we accept easily, 2 coincidences we raise an eyebrow at, 3 in a row, and suspicion settles in like a shadow. 4 or more, and our instincts begin to rebel against the mathematics, whispering that something unseen must be guiding events. With 3 divided by Atlas, this psychological threshold is being tested in real time. What at first felt like an ordinary interstellar visitor has piece by piece assembled itself into a puzzle too orderly for comfort. The first improbability is spatial, the inclination. Interstellar objects should not care about the ecliptic. Their orbits are shaped by distant stars and gravitational tides in the Milky Way. Yet Atlas entered with an inclination of just 5 degrees, sliding almost flush with our planetary plane. On its own, this is a curiosity, not a crisis. But it sets the stage. The second improbability is temporal. The Mars flyby in early October 2025. Out of countless paths it could have taken, Atlas's trajectory places it near enough to the red planet to allow robotic observers to turn their cameras outward. Again, not impossible. But 2 coincidences now sit side by side. The third improbability is geometric. A perihelion distance close to 1 astronomical unit, nearly the same scale as Earth's inhabits. Convenient for ground-based instruments, convenient for study. A third coin flip landed heads. The fourth improbability is observational. The blackout behind the sun, perfectly timed to cloak the most critical weeks of activity. A fourth coin flip, the same result. Now the scorecard of improbabilities begins to weigh heavily. Probability theory teaches that independent events must be multiplied, not added. If each coincidence is given a modest probability, its product shrinks rapidly towards zero. What was tolerable as an isolated quirk becomes intolerable as a sequence. This is why scientists find themselves returning, obsessively, to orbital models, searching for overlooked explanations. Is there a hidden correlation, a gravitational nudge, a bias in discovery methods that makes these alignments less improbable than they seem? Such questions reflect the discipline of controlled skepticism, the refusal to declare miracle or message until every natural explanation is exhausted. And yet the obsession does not go away, because when logic sees a wall of improbabilities, it cannot simply turn away. The scientist becomes like a chess player staring at a board where the opponent makes flawless moves. The rational voice says, "Perhaps it is luck." The logical whisper replies, "But luck cannot repeat itself forever." This whisper is not hysteria. The mind struggles to reconcile mathematics with intuition. It is the tension of why ni ko kiem swat, allowing doubt, but refusing panic. This is why some describe Atlas as an experiment in our own psychology as much as in astrophysics. The object challenges not only our instruments but our patience. How long can we maintain calm skepticism while anomalies pile higher? How disciplined can we remain when logic itself begins to itch with discomfort? In a world of headlines, the temptation is to leap to the extraordinary. But science demands something harder: to stand still in the storm of improbability, to measure quietly, and to wait. The irony is that this restraint is its own form of obsession. The very act of scoring anomalies night after night, running simulations again and again, reveals how deeply Atlas has captured our attention. Scientists claim calm, but their notebooks tell another story. Dozens of probability tables, dozens of model runs, endless recalculations of what are the odds. This is the paradox of controlled skepticism. It looks like detachment, but beneath the surface, it burns with relentless focus. And perhaps that is the deeper significance of Atlas. Beyond whether it proves natural or not, it has forced us to test the limits of our logic. It has shown us how quickly coincidences multiply into questions, and how fragile the boundary is between chance and design. Whether or not the object carries intention, it has already delivered a message that vigilance is not optional, and that science must learn to live with discomfort when improbabilities line up too cleanly. When we speak of improbability, it is easy to reduce everything to numbers, percentages on a page, decimals sliding towards zero. But the real weight of improbability is not mathematical alone. It is psychological, philosophical, and, in the case of 3I divided by Atlas, profoundly strategic. What unsettles observers most is not simply that the odds are small, but that each improbable feature lands precisely where it matters most. It is as though the cosmos has written its script in the language of maximum visibility and maximum ambiguity. Take the Mars encounter in early October 2025. Had Atlas passed near Neptune, few would have noticed. Had its perihelion been far outside Earth's range, the instruments most of us rely on would never have tracked it. Had its blackout not aligned with the most critical observational window, we would not speak of it at all. The improbability is not just in the raw statistics. It is in the alignment of significance, the way each oddity is optimized to provoke attention. That optimization is what turns ordinary improbabilities into an extraordinary chain. Controlled skepticism asks us to quantify this, but logic cannot help feeling the pull of narrative, a pattern that looks too perfect to ignore. In the metaphor of orbital chess, this is where the game grows unbearable. Imagine a sequence of moves where every piece advances to exactly the right square, each one constraining your options, each one denying you relief. It is not that any single move is illegal, it is that the accumulation feels like checkmate written in slow motion. Atlas does not break the rules of physics. It plays within them, but with such precision that the board itself feels manipulated. This is the essence of logic obsession, the recognition that the rules allow what is happening, but the probability that the rules alone created it dwindles with every passing move. The discipline demanded here is extraordinary. To sit in the observatory, night after night, and record data with a straight face while your inner voice insists that you are watching a pattern unfold that requires a special kind of patience. Controlled skepticism is not about denying the whisper of suspicion. It is about letting the whisper remain a whisper until evidence raises its volume. This is what separates vigilance from hysteria. Anyone can be dazzled by a strange light curve. Few can chart it for months, scoring each anomaly while resisting the temptation to name it prematurely. And yet, we must admit the cost. Discipline does not erase obsession, it masks it. Every scientist who logs another data point on Atlas is playing two games at once. One on the page, where numbers remain cold and careful, and one in the mind, where coincidences stack like weights on a fragile scale. Each time the data confirms the trajectory, each time the glow remains asymmetric, each time the blackout draws closer, the burden grows heavier. Controlled skepticism becomes not just a method but a survival skill, the ability to keep working even as logic gnaws at your composure. For the public, this paradox is difficult to grasp. They ask for simple answers. Is it alien or not? But science, bound by discipline, cannot satisfy that hunger. The true answer, at least in this stage, is that we are living through a chain of improbabilities that strain the limits of chance. That is not a declaration of intention. It is a declaration of unease. And perhaps, unease is the most honest posture we can take, because in that unease lies the recognition that the universe is not obliged to make its workings comfortable for us. So what does 3i divided by Atlas teach us, here at the edge of logic? It teaches that coincidence, when compounded, becomes a question mark large enough to eclipse certainty. It teaches that skepticism, when disciplined, can hold the line against hysteria, even as obsession simmers beneath. It teaches that vigilance is not merely about gathering data, but about mastering ourselves, our instincts, our impatience, our craving for narrative. And finally, it teaches that improbability itself is not an answer, but a summons, to look harder, to think sharper, to refuse the easy story in pursuit of the true one. In the end, the improbable cascade of Atlas may dissolve into a natural explanation, or it may not. But either way, the lesson will endure. The next time the chessboard lights up, the next time a piece moves too perfectly, we will be ready with our skepticism, our logic, and our discipline. The game is not over, the board remains set, and 3i divided by Atlas, whether wanderer or messenger, has reminded us that in the universe, the difference between coincidence and choreography may be the thinnest, most haunting line of all. Imagine following a car down a city street at night. Its headlights cut a path, you track its every move, your camera records each turn. Then suddenly, the car makes a sharp corner into an alley, drowned in shadow. Your camera cannot follow. For a few minutes or a few hours you are blind. You do not know if the car stalled, accelerated, or vanished altogether. That helplessness, that breathless pause, is exactly what astronomers face when 3i divided by Atlas swings behind the Sun in late October 2025. We call it a blackout. But the word does not capture the tension. It is not just darkness, it is enforced silence, a cosmic no-man's land where even our best instruments must surrender. From Earth, the geometry is unforgiving. As Atlas approaches perihelion, its closest distance to the Sun, just under 1 astronomical unit, the line of sight for every telescope runs headfirst into solar glare. Photons from the Sun flood detectors, drowning out the faint light of the interloper. No photometry, no spectroscopy, no astrometry survives the assault. Hubble cannot see within 50 degrees of the Sunday. Ground-based observatories are blinded even sooner. For nearly 4 weeks, Atlas will hide in plain sight, bathed in the Sun's radiance but invisible to us. It is as if the stage lights of the universe have been turned up so high that the actors vanish in the glare. What makes this silence so unbearable is the timing. The blackout does not come at a trivial moment. It arrives at the climax. This is when comets transform, shedding mass, venting gases, sometimes fracturing under solar heat. This is when anomalies reveal themselves most clearly. Sudden, brightening, unexpected trajectory shifts. The fingerprints of forces we do not understand. And this is precisely when we will not be watching. The data gap is not a technical inconvenience. It is a narrative hole, a missing chapter in the story of Atlas. When the object emerges in late November, we will not know what it did in the shadows. We will only see the aftermath, like detectives arriving at a crime scene long after the act, forced to infer from the debris. The emotional weight of this gap is heavy. Scientists are not accustomed to helplessness. They build bigger telescopes, launch satellites, and push instruments to extremes. But no technology can erase the Sunday. For once, all their tools are mute. This is where the sense of helplessness becomes palpable. You can simulate, You can model, but you cannot see. The silence is absolute. And yet, paradoxically, it is in this helplessness that the story becomes most gripping. Because what is hidden may matter more than what is shown. The blackout is not empty time, it is suspense embodied, a cliffhanger written into the physics of orbital geometry. And so the world waits. October slides into November. The object vanishes. Our screens go blank. Observatories mark their calendars with a kind of frustration. Resumes visibility in late November. We are left staring at the sun itself, knowing that beyond its glare, a question mark glides unseen. The silence before the reveal is not peaceful, it is charged. Every day of blackout is a reminder that the cosmos can still withhold its secrets, even from a species that has reached across the stars. The silence of the blackout is not merely observational, it is forensic. To lose sight of 3I divided by Atlas in late October 2025 is to lose the very evidence that would settle some of the most pressing questions about its nature. Every discipline of astronomy takes a hit. Photometry, the precise measurement of light curves, falls flat. Without it, we cannot track sudden brightening or fading that might hint at fragmentation. Spectroscopy, the chemical fingerprinting of gases and dust, is drowned. Without it, the anomalous dominance of CO2 remains unresolved. And astrometry, the exact plotting of its orbit against background stars, vanishes into noise. Without it, we cannot confirm whether Atlas remains on its predicted path or drifts with unexplained accelerations. In one sweep of geometry, the sun erases 3 of our most vital tools. For scientists, this is a nightmare dressed in sunlight. They know exactly what they are missing, but they cannot stop the loss. It is as though a surgeon had to operate blindfolded, knowing that the most crucial arteries might tear in those hidden moments. Worse, the blackout coincides with the very weeks when interstellar comets are most dynamic. Close to perihelion, they face the full furnace of solar radiation. Some disintegrate entirely, others split into fragments. Still others reveal unexpected propulsion as gases vent at new intensities. These are the moments when mysteries unravel, and for Atlas, they will happen behind the curtain. This knowledge gnaws at astronomers. The discipline of science demands patience, but patience is not the same as peace. Researchers sit in control rooms, running simulations again and again, projecting what might occur during the blackout. One model predicts a flare in brightness by a factor of 10. Another predicts a sudden fading, as if Atlas sheds its outer layers. Another still suggests a small but measurable change in trajectory, hinting at non-gravitational forces. Each scenario is plausible. None can be confirmed. Logic becomes an obsession, trapped in the silence of lost data. This is the source of the deep, anxious thrill. It is not the thrill of discovery, but the anxiety of waiting for a reveal you cannot control. Every day that passes without data tightens the suspense. Scientists wake each morning knowing nothing has changed. They are still blind, and yet the weight of what might be happening behind the sun grows heavier. The longer the silence lasts, the more the mind fills the void with possibilities. Some cling to hope. Maybe Atlas is stable, behaving like a comet should. Others fear catastrophe. Perhaps it has fractured, leaving only a swarm of fragments to emerge weeks later. Still others entertain the most controversial thought, that if Atlas is not entirely natural, the blackout could be its chosen moment to maneuver unseen. That last possibility, though speculative, adds an extra layer of unease. Because if Atlas were to alter its course behind the sun, no one on Earth could know until late November. The orbit would appear seamless when it re-emerges, but any subtle deviation would reveal itself in hindsight. In the language of orbital chess, the blackout is a move we cannot see, a hidden hand shifting a piece while our eyes are forced shut. The very geometry of the solar system conspires to deny us oversight, and that denial feels deliberate even when we know it is not. Here, the sense of helplessness deepens. Astronomers are used to fighting their limitations with ingenuity. Adaptive optics to tame the atmosphere, coronagraphs to blot out starlight, spacecraft to escape Earth's distortions. But no ingenuity can erase the sun's glare from this geometry. No telescope can stare through its fire. For all our technology, for all our reach into space, the blackout reminds us that we remain fragile observers, subject to blind spots carved into the heavens. It is a humbling, almost humiliating realization. And yet, paradoxically, this helplessness makes the story more human. Because in our inability to see, we mirror the ancient skywatchers who also waited through gaps in knowledge, filling silence with speculation, wonder, and dread. The blackout is not just an astronomical event, it is a return to the primal condition of curiosity, the long pause before revelation, when the night feels longest and the questions deepest. It is here, in the charged stillness of October and November 2025, that the tension surrounding Atlas reaches its peak. When November drags toward its end and the glare of the sun finally loosens its grip, 3i divided by Atlas will re-emerge, but it will not be the same object that disappeared weeks earlier. Something will have changed, whether in brightness, trajectory, or chemistry, and those changes will tell us the story of what happened in the shadows. Yet the most unsettling truth is this: we will never know the details. The blackout is a permanent scar in the record, a lost chapter that no reconstruction can fully restore. Scientists will compare the before and the after, like forensic investigators arriving late to a crime scene, but the act itself will remain hidden forever. That permanence is what makes the silence so haunting. For those in the field, this gap is both a technical obstacle and a psychological wound. They will measure Atlas's new trajectory with extreme care, hunting for the faintest signs of non-gravitational acceleration. They will study its coma and spectrum, searching for traces of fragmentation or unusual venting. They will chart its light curve night after night, wondering if the missing weeks contained a flare, a collapse, or a maneuver. But they will do so always with the knowledge that the decisive evidence is gone. The blackout cannot be undone. The cosmos has imposed a limit, and human ingenuity, for all its brilliance, cannot cross it. That knowledge feeds the emotion of helplessness. We pride ourselves on progress, on bending nature to our will, on inventing tools that pierce the invisible. And yet, here is a simple geometric fact: an object passing behind the sun that reduces us to helplessness. The most advanced satellites are blind. The most powerful telescopes are silenced. We are reminded, sharply, that there remain domains where we are not in control. This helplessness is not defeat, but it stings. It forces humility, a recognition that vigilance is not omniscience. And still, the anxious thrill does not end when Atlas reappears. If anything, it intensifies. Because the moment of emergence is not a resolution, it is a revelation laced with suspense. What will we see? A comet brighter, swollen with solar heat? A broken swarm of fragments? A trajectory unaltered, or one shifted by an unseen push? The days after the blackout will feel like the lifting of a curtain after a long intermission. But instead of applause, the audience will hold its breath, scanning the stage for signs of what was missed. For the public, this makes Atlas's blackout a drama unlike any other. It is the universe itself, withholding information, forcing us into a suspense we cannot resolve on demand. In a culture that craves instant answers, the blackout demands patience, and patience breeds tension. People will speculate wildly in the silence, some imagining catastrophe, others envisioning secrets revealed. But speculation is all they will have until the curtain lifts. This is why the blackout feels cinematic. It is the scene where the hero vanishes into shadow, and the audience must wait, heart racing, to see what emerges. And therein lies the paradoxical gift of this silence. By denying us data, Atlas has heightened our awareness. Every detail after its return will be scrutinized more fiercely because of what we missed. Every photon captured will feel heavier with meaning. The absence of information, strange as it sounds, has increased the value of information. This is the logic of suspense. What is hidden sharpens the hunger for what is revealed. In the grand narrative of 3i divided by Atlas, the blackout is not just a pause. It is the heartbeat of the story, the moment where tension peaks, where helplessness collides with curiosity, where science itself is forced into silence. When the object finally steps back into view, we will all look harder, think sharper, and question deeper. The silence has primed us for vigilance. And maybe that is the lasting lesson. That even in an age of telescopes and satellites, there are moments when the universe closes its curtain and leaves us waiting. That waiting is uncomfortable. It feels powerless. But it is also essential, because in that helpless pause, we rediscover something science too easily forgets. Suspense is not the enemy of knowledge. It is the fire that drives us to seek it. And in the silence before the sun, 3i divided by Atlas has given us exactly that fire. Imagine hearing a knock at your front door in the middle of the night. Your heart leaps. Curiosity sparks instantly. Who could it be? But your hand does not immediately turn the knob. You freeze, listening for patterns, another knock, a shuffle of feet, some evidence that justifies opening the door. This tension between desire and discipline, between the fire of fascination and the ice of caution, is the posture science must adopt when revisiting the so-called mothership hypothesis around 3I divided by Atlas. The knock is real. The timing is uncanny. The temptation to fling the door wide is overwhelming. But the scientific instinct insists, wait, test, measure. Why does the word mothership return every time interstellar objects defy our expectations? Because it embodies the most tantalizing possibility, that we are not alone, that something has chosen to pass close, to reveal itself in just enough detail to stir suspicion. With Oumuamua in 2017, it was the cigar-like shape and unexplained acceleration. With Borisov in 2019, the chatter faded because its messy chemistry fit the comet mold. But now, with Atlas in 2025, the whispers rise louder. Too many of its features feel choreographed. A near-ecliptic entry, a waypoint near Mars in early October, a perihelion close to Earth's observational sweet spot, and then, just when the show reaches its climax, a blackout behind the Sunday. To the imagination, this is not a chance. It is an itinerary. It is reconnaissance. It is, in the most provocative sense, design. But imagination is not science. This is where self-restraint must counterbalance curiosity. To revisit the mothership hypothesis responsibly, we must frame it not as a conclusion, but as a set of conditional statements. If Atlas exhibits short-duration light spikes inconsistent with natural outgassing, then engineered activity becomes a viable consideration. If its trajectory post-blackout diverges measurably from gravitational models beyond what sublimation can explain, then intentional maneuvering cannot be ruled out. If its spectral lines reveal metals, alloys, or other compounds absent in cometary chemistry, then natural explanations weaken. Each if is a gateway, but none are crossed without evidence. This logic is the shield that keeps science from collapsing into fantasy. The mothership hypothesis is seductive precisely because it answers our hunger for agency in the cosmos. A comet is silent, a ship is purposeful, but science must resist the premature leap from anomaly to agency. The job is not to declare Atlas a vessel. The job is to define the conditions under which such a claim could ever be justified, and to measure ruthlessly against those conditions. This balance between curiosity and self-restraint is not sterile. It is alive, humming, electric. Scientists feel the same magnetic pull as the public. They want to believe the knock at the door is extraordinary. They want to imagine that the blackout conceals maneuvering, that the asymmetric glow is a radiator, that the trajectory is a flight plan. The questions bubble. What if we are being observed? What if this is deliberate? These questions are not weaknesses, they are fuel. They keep telescopes pointed, simulations running, and papers written. But each question must be tethered to the hard floor of evidence. Otherwise, curiosity becomes conspiracy. And there is something deeply human about this tug of war. We have always been drawn to the extraordinary while fearing our own gullibility. The mothership hypothesis is not an exception, it is a mirror. It shows us how our minds strain toward wonder while our methods insist on caution. That duality is what makes Atlas such a perfect test. It excites, but it also restrains. It knocks, but the door stays closed. The beauty of framing it with if, then, is that it transforms an incendiary idea into a scientific tool. Instead of shouting Atlas is a mothership, the careful posture says, if X happens, then the mothership hypothesis earns weight. If not, the score remains low. This makes the hypothesis measurable, gradable, and scoreable like any other. It becomes part of the anomaly scale, not an outlier. It lives inside the disciplined system instead of outside it. And that is how science should treat its most daring ideas, not by exiling them, but by demanding that they survive the crucible of evidence. So we stand at the threshold, the knock echoes, the world leans closer, curiosity pounding in its chest. But the doorknob remains still. Scientists will not open it until the data compels them. That is not cowardice, it is integrity. And if the door ever swings wide, it will not be because of imagination's pull, but because evidence forced our hand. Until then, the mothership remains a possibility, held at arm's length, a story we suspect, a question we dare to ask, but a conclusion we will not yet claim. Curiosity, once ignited, does not fade easily. The mothership hypothesis lingers in the background of every conversation about 3I divided by Atlas, not because scientists want to sensationalize, but because the object itself keeps producing anomalies that tempt the imagination. Yet, what distinguishes rigorous inquiry from idle speculation is the discipline of self-restraint. It is one thing to wonder, another to conclude, and in the gap between those two lies the heart of scientific integrity. To keep the hypothesis alive without letting it dominate, researchers turn it into a conditional framework. They phrase it with precision. If Atlas displays unusual short-term variability in brightness during the weeks after re-emergence, then the idea of technological modulation must be weighed. If its trajectory deviates by even fractions of an arc-second beyond what models predict, then intentional propulsion must enter the discussion. If future instruments detect artificial spectral lines, then we must elevate the hypothesis. These are not conclusions, they are checkpoints. Each is like a gate on a mountain trail. You may reach the first, you may even pass it, but the summit remains distant. To climb responsibly, you must stop at each gate, measure, and decide whether to go further. This measured climb is essential, because without it, the slope becomes a landslide of fantasy. History offers examples. In the 1,960 seconds, the first pulsars were so regular they were nicknamed LGM for little green men. The temptation to label them technological was overwhelming, yet patience revealed them as neutron stars. The lesson is sharp. Curiosity is the spark, but self-restraint is the harness. Only by holding both together did science avoid a false conclusion. With Atlas, the same balance must hold. The anomalies invite the question of a mothership, but the evidence has not yet earned the answer. And here lies the paradox. The very act of restraint deepens the obsession. By refusing to leap, scientists spend more time scoring, modeling, and simulating. They run countless orbital projections, each one a quiet test of what if. They calculate non-gravitational forces, asking how much sublimation could mimic a maneuver. They study the asymmetry of its glow, asking how long a natural jet could sustain a pattern. Each calculation is a way of holding the hypothesis at arm's length, without dropping it, without clutching it. It is a strange dance, curiosity and caution moving together, neither allowed to lead. For the public, this stance can feel unsatisfying. They crave certainty. Is it natural, or is it a ship? But certainty is premature. What science can offer instead is transparency, a ladder of conditions, each one explicit. If Atlas meets none, the mothership hypothesis remains an unproven curiosity. If it meets some, the score climbs. And if one day it crosses the highest threshold, then restraint itself will deliver the most profound revelation in human history. Until then, the discipline of if-then preserves both credibility and imagination. The blackout behind the sun only heightens this dynamic. During those 4 weeks of silence, anything might happen, and nothing can be seen. Curiosity screams, "What if this is the maneuver?" Self-restraint replies, "Wait until November, measure carefully, then decide." When Atlas emerges, telescopes will search not only for the comet, but for the faintest hints that something changed while it was hidden. That search itself is a kind of confession. Even while restrained, science cannot resist its curiosity. The mothership is the forbidden thought that drives deeper vigilance. This is why the hypothesis remains important, not because it is proven, but because it sharpens our methods. It forces scientists to articulate what counts as evidence, what thresholds must be crossed, and what anomalies demand attention. It disciplines curiosity into a framework, making the most provocative idea part of the same orderly system that judges every anomaly. And in doing so, it demonstrates that science's strength is not in suppressing questions, but in demanding proof before granting answers. So the knock at the door continues, echoing through October and November. We hear it, we wonder, but the knob does not turn. The door remains shut, not in fear, but in patience. And behind that patience lies a promise that if the knock ever becomes unmistakable, we will open it with both curiosity and certainty in hand. The most powerful quality of the mothership hypothesis is not that it answers our questions, but that it forces us to ask sharper ones. Every time 3I divided by Atlas performs a move that looks suspicious, its waypoint near Mars, its asymmetric glow, its vanishing act behind the sun, the hypothesis hovers in the background like an uninvited guest. It is never officially welcomed, but it is never fully dismissed either. Instead, it becomes the silent standard against which all evidence is tested. Curiosity keeps the guest in the room. Self-restraint prevents it from speaking too loudly. This silent presence changes how scientists behave. Suddenly, every small measurement matters more. A faint fluctuation in brightness is not shrugged off, it is logged, double-checked, compared across instruments. A fractional deviation in orbit is not waved away, it is modeled, recalculated, and scrutinized for days. Even the chemistry of the coma, saturated with carbon dioxide, is reconsidered not just as a cometary quirk, but as a possible functional signature. In this way, the mothership hypothesis elevates the vigilance of science without hijacking its discipline. It does not dominate the data, it deepens our hunger to interrogate it. And yet, restraint remains the anchor. Because history has warned us what happens when restraint fails. Countless mysteries once hailed as signals of alien intelligence, radio bursts, repeating pulses, anomalous lights, later revealed themselves as natural phenomena. The danger is not in being curious, the danger is in declaring too soon. With Atlas, the temptation is sharper than ever. Its path looks planned, its timing looks precise, its blackout feels theatrical. Everything about it whispers design. But until the evidence crosses thresholds set by the if-then framework, science must keep the whisper a whisper. This is not weakness, it is strength. The ability to imagine boldly while concluding cautiously is the very essence of scientific maturity. The mothership hypothesis, if treated recklessly, would collapse into fantasy. Treated carefully, it becomes a tool, one that sharpens our methodology and forces us to articulate standards of proof. It is a mirror for our own process, reminding us that the pursuit of truth requires both the courage to ask and the discipline to wait. What happens, then, if Atlas emerges from its blackout unchanged? If its orbit follows the models? If its brightness curve fits natural sublimation? If its chemistry remains comet-like? Then, the mothership hypothesis retreats, not defeated but dormant. It waits for the next object, the next anomaly. Science does not mourn its retreat, because hypotheses are not prophecies. They are tools, and tools are set aside when not needed. But if Atlas emerges with deviations, if the data insists on forces we cannot explain, then the hypothesis advances another step on the scale. The knock at the door grows louder. The hand on the knob feels heavier. Either way, the story of Atlas has already changed us. By inviting the question, by surviving in the tension between curiosity and restraint, it has redefined how we approach interstellar visitors. No longer will we see them as passive wanderers alone. We will measure them as potential messengers, scrutinize them as possible scouts. We will ask more, test more, doubt more, and in doubting, we will learn more. The mothership hypothesis may or may not prove true, but it has already proven useful, and so the door remains closed for now. The knock continues, steady, patient, unanswered. Our curiosity strains to fling it open. Our discipline holds our hand steady on the knob. This balance is the final lesson of Atlas, that knowledge is not found in rushing toward the extraordinary, nor in dismissing it outright, but in walking the thin line between wonder and restraint. If one day the door opens, it will be because the evidence turned the handle, not because our impatience did. And when that moment comes, if it comes, the world will not be surprised. We will have been waiting, listening, and holding our breath since the night of the first knock. Imagine a fighter jet slipping into the blind spot of enemy radar. For a moment, it disappears, not because it ceased to exist, but because it has chosen the one angle that shields it from detection. The tactic is not brute force, but stealth. Now replace the jet with 3i divided by Atlas, and the radar with our telescopes. When Atlas passes behind the Sun in late October 2025, it enters exactly such a blind zone. Whether by accident of orbital mechanics or by intent, it achieves the same effect, concealment. And for those watching, the tactic feels less like a coincidence and more like a maneuver drawn straight from the playbook of cosmic strategy. Staying tin-tao in the face of such a move is essential. The temptation is to let imagination run wild, to call the blackout deliberate. But science demands calm clarity. First, acknowledge the geometry. The Sun's overwhelming brightness saturates detectors. Hubble cannot observe within 50 degrees of solar elongation. JWST, stationed at L2, is equally blind to objects near the Sunday ground-based observatories fare worse. From October 29 through late November, Atlas will vanish into this glare. That fact alone requires no agency. It is the inevitable result of physics, yet the tactical implications are unavoidable. If one were to design a moment to slip unseen, this would be it. Here, the analogy with military stealth deepens. In warfare, concealment behind terrain or electronic noise is not absolute. Once the fighter jet re-emerges, radar reacquires it. Similarly, once Atlas passes out from behind the Sun, its orbit will be tracked again with precision. This is where quit d'Oan becomes critical. Astronomers can state with certainty, even if Atlas hides during a blackout, orbital truth will reveal whether it drifted or maneuvered. The Sun may block our eyes, but it cannot erase gravity. When Atlas reappears, any delta V, any deviation, any stealth move will stand naked in its post-blackout trajectory. The tactic buys silence, but not immunity. And this is the dual edge of the strategy. If Atlas is only a comet, its blackout is nothing more than geometry playing tricks with our line of sight. But if it were more than that, if it carried intent, then the Sun provides the perfect cover for action. Engines could fire, fragments could separate, orientation could shift, and no one on Earth would witness it directly. All we would see is the aftermath, the altered path after late November. That is why the blackout feels tactical, even if no agency is involved. It is a reminder that concealment and suspicion often grow from the same soil. For the scientific community, this moment requires calm vigilance. The narrative of behind-the-sun tactics may sound sensational, but the analysis must remain disciplined. Telescopes will be ready in December to measure Atlas's re-emergence. Models of its predicted orbit are already published, with margins of error calculated. The decision is not whether to speculate, but whether to test. That is the line between curiosity and hysteria. Staying Tintau means acknowledging the strategic appearance of the blackout without surrendering to it as proof. Being quit d'Oan means committing now. When the data returns, we will measure relentlessly, and the truth will not hide. The chessboard of orbital dynamics is impartial. The Sun can conceal for weeks, but the pieces will reveal themselves when the curtain lifts. Atlas may look like a stealth jet for a time, but in the end, gravity will betray every move. This is not faith, it is orbital mechanics, unyielding, unforgiving. And so, with calm clarity and decisive intent, astronomers prepare. The game will resume in November. The tactic may be stealth. The response must be disciplined. In military strategy, concealment always triggers the same haunting question. What happened when we couldn't see? A fleet disappears beyond the horizon. A submarine dives beneath sonar range. A fighter slips into cloud cover. Every commander knows the unease of that blind moment. Did the fleet change course? Did the submarine alter depth? Did the jet maneuver unseen? The answers only arrive when the hidden force resurfaces. With 3I divided by Atlas, the scientific community faces this exact dilemma. For nearly 4 weeks in late 2025, the object vanishes into the furnace of the Sun's glare. And when it returns, the decisive question will be, did it merely endure natural heating like any comet, or did something change in the dark? Maintaining clarity in the face of this silence is not a suggestion. It is a necessity. The blackout is unavoidable. The geometry of the solar system ensures it. The real danger lies not in losing the view, but in letting imagination fill the gap unchecked. Some will rush to declare, this is proof of intent. If you wanted to maneuver unseen, this is when you'd do it. Others will dismiss it out of hand. It's nothing more than geometry. The disciplined response is more sober. Both possibilities exist, but neither is confirmed. The only correct course is preparation, not proclamation. And preparation means building the tools, refining radar calibrations, tightening orbital models, mapping astrometric grids, so that when Atlas emerges, the data can settle the debate without ambiguity. This is where decisiveness matters. Science cannot remain suspended in endless maybe. Observers must define in advance what counts as evidence. The conditions must be drawn like lines in sand. If Atlas emerges precisely where the orbital models predict, then the blackout was nothing more than a geometric consequence. If it reappears measurably off course, if the difference cannot be explained by outgassing or natural forces, then suspicion escalates. The choice is not whether to decide, but when and on what basis. The basis must be conditions, not speculation. Just as in military intelligence, A stealth move is only confirmed when the jet reappears in a position inconsistent with prior trajectory. The principle is the same here. The public, of course, will demand certainty during the silence. What's happening right now? They will ask. The truthful answer is uncomfortable. We don't know, but science can promise something stronger than instant answers. It can promise decisive ones when the time comes. Orbital mechanics is an incorruptible witness. Atlas may vanish from our sight, but gravity records everything. Any delta V, any intentional burn, any stealth maneuver in the glare will manifest as a scar in its post-blackout trajectory. Those scars cannot be hidden. This blend of calm clarity and firm decisiveness transforms the blackout from a period of helplessness into a structured test. Instead of indulging rumors, observatories focus on readiness. Instead of being paralyzed by what cannot be seen, they sharpen their tools for what can be measured later. The blackout becomes less a mystery and more a proving ground. The tactic may look like concealment, but the counter-tactic is patience fused with precision. And so the weeks of silence unfold. October fades into November. Atlas is swallowed by the solar glare. Yet in control rooms across the world, there is no panic. There is tension, yes, but it is disciplined tension. Astronomers know exactly what they are waiting for. They know the coordinates, the margins of error, the data points that will decide the narrative. This is what clarity paired with decisiveness looks like. Eyes steady, thresholds defined, no hysteria, no denial, just preparation. In military language, the strategy is simple. Concealment invites suspicion, but reappearance reveals truth. Atlas may look like it is playing stealth tactics behind the Sunday. Science responds with its own tactics, measured, methodical, and unflinching. Wait, measure, decide. When late November comes and the object steps out of the sun's shadow, the results will speak louder than speculation ever could. In warfare, concealment is always temporary. A submarine cannot remain below sonar forever. Batteries drain, and oxygen runs low. A fighter jet cannot stay invisible. The radar sweep eventually circles back. Even the sun, for all its blinding power, is no exception. Its glare can erase a comet from our sight for weeks, but it cannot erase the evidence of what happened during that time. That is the paradox of the so-called behind-the-sun tactics. They may frustrate us, they may heighten suspicion, but when 3I divided by Atlas re-emerges in late November 2025, orbital mechanics will tell us whether anything truly occurred in the shadows. This is where clarity matters most. The blackout itself does not prove maneuver, nor does it prove innocence. It is only a curtain. Remaining clear-eyed means remembering that concealment is not equivalent to intent. Every comet near perihelion disappears for some period. The discipline lies in refusing to label the silence as anything more than geometry until the data after the blackout confirms otherwise. But decisiveness requires us to set conditions in advance, so that once the curtain rises, there is no hesitation in judgment. Did Atlas's path remain consistent with gravitational predictions? Did its coma expand or contract in ways fully explained by sublimation? Did its rotation or brightness change in a way out of step with natural physics? These are not vague questions, they are measurable thresholds. When Atlas steps back into the light, each one will be tested. This dual posture, calm and firm, transforms suspense into structure. The blackout may feel like a stealth maneuver, but science treats it as an experiment. If the data after November aligns with models, then the tactic was nothing more than a coincidence of orbital geometry. If the data diverges, then suspicion escalates. Either way, the decision will not be driven by imagination but by metrics. This is what decisiveness looks like in scientific practice, defining the criteria before the test, so that emotion cannot bias the result. For the public, the suspense will be dramatic. The silence of October and November will become a breeding ground for speculation. Some will declare that Atlas used the blackout to alter course, to hide its true nature. Others will insist it is just another comet, and that the excitement is misplaced. Scientists, however, will hold to their line. They will not indulge hysteria, but neither will they dismiss anomalies prematurely. Instead, they will say, if the object returns on track, then the case is closed. If it does not, then we proceed further. That clarity of stance is not indecision, it is discipline. The strategic metaphor remains powerful. In chess, a queen may disappear behind a wall of pawns, But when it emerges, its position betrays whether it hid for defense or prepared for attack. In the same way, Atlas cannot conceal forever. Its trajectory is the board, gravity, the referee, and orbital data, the ultimate checkmate. Whatever happened in the glare, the mathematics will reveal. The sun may shield our eyes, but it cannot shield the truth. And so the world waits, instruments prepared, thresholds defined. When the first post-blackout measurements arrive, the suspense will break. Within hours, astrometric points will show whether Atlas's path remained loyal to gravity or bent to something else. Within days, light curves and spectra will tell whether it flared, fractured, or persisted. Within weeks, the verdict will be clear. The tactic of concealment will have run its course, and the counter-tactic of patient measurement will deliver the result. This is the ultimate lesson of behind-the-sun tactics. Concealment may unsettle, but it cannot deceive. Suspense may silence us, but it cannot silence physics. In the end, Atlas may look like a stealth jet slipping into a blind zone, but when it emerges, the universe itself will render judgment. And that judgment will not come from rumor, but from the decisive clarity of data. Imagine walking into a desert, expecting to find a well of pure water, only to discover instead a bubbling fountain of soda. The shock would stop you in your tracks. This is the kind of astonishment astronomers felt when they analyzed 3I divided by Atlas and found that its outgassing was dominated not by water vapor, as every cometary model would predict, but by carbon dioxide at a staggering ratio of 8:1. To put it plainly, for every molecule of water, there were 8 molecules of CO2 escaping into space. In the language of comet science, this is upside down, inside out, and completely unexpected. Why is this so astonishing? Comets in our solar system are overwhelmingly water ice. Yes, they contain carbon dioxide and carbon monoxide, but water almost always dominates. When a comet approaches the Sun, the first thing to sublimate, meaning turn from ice to gas, is H2O. Spectroscopic studies of dozens of comets confirm this pattern. Ratios vary, but water is always king. Carbon dioxide typically lags far behind, contributing a fraction of the gas output, yet with Atlas, the ratio is inverted. It is as if we found an ocean where desert maps predicted none. To make sense of this, let's translate the jargon. Astronomers use spectroscopy, the measurement of light spread into colors, to identify gases in a comet's coma. The glowing cloud around its nucleus. Each molecule absorbs and emits light in unique ways, creating a fingerprint. For water vapor, the fingerprint is strong in the ultraviolet and infrared. For carbon dioxide, it lies in specific infrared bands. By pointing telescopes at Atlas before its blackout, scientists could read these fingerprints. What they saw was clear. CO2 lines blazing, water lines faint. The ratio? Roughly 8:1. For experts, this ratio feels almost alien. To the public, the easiest way to grasp it is through diet. Imagine lining up 8 cans of soda next to 1 glass of water. That's Atlas. Our solar system comets, by contrast, look like 8 glasses of water with a single can of soda. The inversion is so stark that it leaves little room for comfort. Something about Atlas is fundamentally different. Now, a cautious mind must ask, could the data be wrong? Instrumental error, calibration issues, and background contamination all are possible. Scientists are trained never to accept shocking results at face value. So the teams checked, recalibrated, and compared instruments. The answer held. Atlas really is gushing carbon dioxide at extraordinary levels. That is why this anomaly is not dismissed but taken seriously. It is not a glitch. It is a property. What could explain it? One natural hypothesis is that Atlas formed in an extremely cold region of its birth system, where CO2 froze out in abundance and water ice was scarce. Another is that its surface lost most of its water long ago, leaving CO2-rich layers exposed. A third suggests that repeated heating cycles in interstellar space altered its chemistry. None of these is impossible, but none fit comfortably either. Each explanation stretches what we know, raising more questions than it resolves. And here is where the astonishment turns into a mix of awe and unease. Because if the ratio cannot be explained easily by natural models, then curiosity inevitably nudges toward the provocative. Could such a composition be intentional? After all, CO2 has useful properties. It can act as a propellant when vented, a radiator for thermal control, or even a shielding gas. To suggest that E sign is dangerous ground, but the data itself invites the question. Scientists may restrain the conclusion, but they cannot restrain the question. This is why the CO2 mystery matters. It is not just a quirk of chemistry. It is a signal, whether natural or not, that Atlas is not like anything we have catalogued before. It demands that we recalibrate our expectations. It forces us to re-examine the building blocks of comets and the assumptions we carry. It leaves us astonished, but also vigilant, knowing that in science, astonishment is often the first step toward discovery. To appreciate just how staggering the CO2 mystery of 3I divided by Atlas is, you need to see it in context. One anomaly is intriguing, but anomalies gain weight when compared against a baseline. Fortunately, astronomers have decades of data on comets within our solar system and two clear precedents for interstellar visitors: Oumuamua in 2017 and Borisov in 2019. Side by side, the contrast makes Atlas look not just unusual but singular. Start with home turf. Our solar system comets almost always tell the same story. Water dominates. When Halley's Comet was studied in 1986, water vapor made up the majority of its coma, with carbon dioxide only a few percent. When Comet 67P divided by Churyumov-Gerasimenko was visited by the Rosetta spacecraft, the results were consistent. H2O was king, CO2 a minor player. Even comets with unusual chemistry rarely invert the ratio. You can find comets where CO2 might reach 1/3 or even half the water content, but never where CO2 outnumbers H2O 8-1. If you line up the data, Atlas is not just off by a margin, it is flipped upside down. Now compare interstellar guests. Oumuamua famously frustrated astronomers because it did not display a coma at all. There were no gases detected, no glowing halo to analyze. Its mystery came from silence. Borisov, by contrast, looked perfectly cometary, water-rich, volatile-rich, and familiar. It behaved like the thousands of solar system comets we already knew. Atlas is different from both. Unlike Oumuamua, it does have a coma, and unlike Borisov, its chemistry is inverted. Out of 3 known interstellar objects, Atlas is the outlier of outliers. For the public, the easiest way to picture this is through cooking. Imagine 3 pots of soup. One pot is bland, you taste almost nothing. Oumuamua. The second pot tastes exactly like the recipe you've always known. Borisov. The third pot, Atlas, hits your tongue with a flavor profile you've never experienced, where the seasoning overpowers the base in ways that make no culinary sense. That is what astronomers are facing, a recipe that defies every cookbook. This is where astonishment collides with caution, because such a radical ratio forces uncomfortable questions. Did Atlas form in a system where water was scarce? That would suggest conditions very different from the protoplanetary disk that birthed our solar system. Or did it lose water through some catastrophic event in deep time, leaving CO2 as the dominant volatile? That would require mechanisms we have not observed in practice. Each natural explanation stretches plausibility, not because they are impossible, but because they require bending too many rules at once. The cautious scientist responds by checking the numbers again. Could the 8-to-1 ratio be skewed by observational bias? Maybe water sublimated at wavelengths we could not capture? Perhaps dust in the coma masked water lines? Yet after multiple instruments confirmed the result, the conclusion hardened. Atlas is genuinely CO2 heavy. The astonishment is not an artifact, it is the object itself. And this, inevitably, draws comparisons beyond natural models. Carbon dioxide is not random in its usefulness. Engineers know it well, as a propellant in cold gas thrusters, as a regulator of temperature, as a medium for energy transfer. To see it dominate so thoroughly in an interstellar visitor raises eyebrows. If one were designing an object that needed to vent, steer, or regulate heat, CO2 would not be a terrible choice. The thought does not prove intent, but it hovers like a shadow over the data. The challenge, then, is how to remain astonished without surrendering to assumption. This is where the balance of emotions matters. Scientists are free to admit their amazement, the ratio is staggering, the chemistry shocking, but they must temper it with vigilance. Astonishment must lead not to fantasy but to deeper investigation. What new models of cometary formation might explain Atlas? What future instruments could resolve whether this chemistry is widespread in interstellar space, or unique to one rogue traveler? What other volatiles might we be missing in the blind spots of our measurements? In that sense, the CO2 mystery is both an invitation and a warning. It invites us to stretch our theories, to imagine planetary nurseries colder and stranger than ours, but it warns us not to leap too quickly into extraordinary conclusions without extraordinary evidence. Atlas may be the strangest recipe we have ever tasted, but science demands we test the ingredients carefully before naming the chef. The true weight of the CO2 mystery lies not only in what it tells us about Atlas, but in how it forces us to rethink the boundaries of possibility. For decades, comet science rested on the assumption that water ice is the universal baseline. Water is abundant, stable, and it dominates cometary physics. Now Atlas arrives with its 8-to-1 inversion, and suddenly the baseline looks fragile. This is where astonishment becomes more than an emotional reaction, it becomes a pivot point for science itself. Consider what this ratio means if we take it at face value. Either Atlas is part of a population of interstellar comets radically different from anything in our solar system, or it is an outlier with a unique history that makes it chemically extreme. The first possibility is breathtaking. If other systems produce comets where CO2 dominates, then our solar system is not the norm, but the exception. It means the chemistry of planetary nurseries is more diverse than we imagined. It challenges the idea that water worlds are universal starting points. In a cosmos where carbon dioxide reigns, the architecture of planets, and even the prospects for life, may unfold along very different paths. The second possibility that Atlas is unique raises different but equally astonishing questions. What could strip a body of water so thoroughly while leaving CO2 intact? Water sublimates more easily than carbon dioxide, so in theory, it should be depleted faster. Did Atlas endure cycles of heating in deep space that selectively removed H2O? Did it collide with another object, exposing CO2-rich layers? Did cosmic rays over millions of years restructure its chemistry? Each scenario strains credibility, but none can be excluded. Each forces us to expand our sense of what is possible in the cold, violent expanse between stars. And then there is the third path, the one scientists mention cautiously, but the public seizes on eagerly. If the CO2 dominance is not natural, could it be engineered? Could Atlas carry a reservoir of carbon dioxide because it serves a function, propulsion, shielding, thermal management? To be clear, the evidence is not there yet. No line of data proves intent, but the sheer oddity of the ratio makes the question unavoidable. And even if the answer is no, asking the question refines our methods. It forces us to define what evidence would actually tip the balance, and what anomalies remain simply curiosities. Here is where caution sharpens astonishment into vigilance. The scientific response is not to declare Atlas is artificial. It is to say, if its chemistry remains consistent after blackout, if the ratio holds under further scrutiny, then we must expand our models. If future interstellar objects show the same inversion, then we may be seeing a new class of comet altogether. And if the anomalies ever extend beyond chemistry into trajectory, into structure, then the conversation changes. This conditional framing keeps astonishment productive. It prevents it from collapsing into speculation, while preserving its power to drive new exploration. For the public, the CO2 story is one of wonder, with a sharp edge. It is easy to be dazzled by the phrase 8-to-1 and imagine spacecraft hidden in icy shrouds. But the real marvel lies in how science translates this astonishment into action. Spectrographs will be recalibrated. Comparative surveys will expand. Missions to track future interstellar visitors will be proposed. The mystery of Atlas becomes a catalyst, pushing astronomy into deeper questions and bolder instruments. This is how astonishment becomes discovery, not by yielding to fantasy, but by building the tools to test it. And so, as Atlas arcs through its journey, the 8-to-1 ratio stands like a beacon. It is both a shock and a challenge. It shocks us by defying the expectations set by every comet we have studied. It challenges us by demanding explanations that stretch beyond comfort. Whether natural or otherwise, it is a signpost pointing toward the unknown. And in science, such signposts are priceless. The story of the CO2 mystery is therefore not only about a comet. It is about us, our willingness to be astonished, our discipline to remain cautious, and our determination to pursue the truth no matter where it leads. Atlas has reminded us that the cosmos still holds recipes we cannot read, ratios we cannot explain, and mysteries that leave us both amazed and on guard. And in that space between astonishment and caution lies the frontier of discovery. Picture a chessboard suspended in the sky, the pieces not carved from wood but sculpted from worlds. Mars sits like a knight on the red squares, Jupiter looms like a towering queen, and the sun itself blazes as the center of the board. Into this game strides three divided by Atlas, not as a pawn drifting aimlessly, but as a piece whose moves demand attention. Every square it touches, every line it crosses, feels like strategy. This is the sensation astronomers describe as orbital chess, and Atlas is playing it with unnerving precision. The suspense lies in the sequence. In early October 2025, Atlas brushes past Mars's orbit, like a knight glancing by the enemy's front line. The geometry is almost too perfect. Its trajectory cuts the red planet's path within a window of weeks when our orbiters are positioned to see. From there, it arcs toward perihelion near Earth's distance from the Sun, vanishing into the blackout. The game pauses. The audience holds its breath. Then, when the curtain lifts in late November, Atlas is already en route to its next waypoint toward the gravitational dominion of Jupiter in 2026. Mars was the opening gambit. Jupiter will be the middle game. Why does this feel so strategic? Because in orbital mechanics, planets are not passive spectators. They are gravitational players, each one bending trajectories like hands nudging chess pieces across the board. Mars is subtle, its mass is small, but its symbolic role is enormous, close to our robots, close to our imagination. Jupiter, by contrast, is the giant of the game. With its massive gravity well, it dominates the outer solar system. If Atlas drifts close enough to its influence, the path could change dramatically, like a queen sweeping diagonally to control the board. The suspense grows from this sequence: Mars now, Jupiter next. It looks less like wandering and more like an itinerary. To translate this into plain terms, imagine planning a road trip. You stop first at a small town, not because it is powerful, but because it sits on the way. Then you head for the metropolis, knowing its highways will pull you in, alter your direction, maybe even decide your next destination. Atlas's path feels like that road trip. Mars is a small town, symbolic, intriguing. Jupiter is the metropolis, inescapable, decisive. The itinerary is written in math, but it reads like a strategy. This is why astronomers talk with both caution and awe. Caution, because orbital mechanics is impartial. Atlas may simply be following a trajectory written by chance billions of years ago, and we are only now recognizing its intersections. Because the alignments are too compelling not to feel intentional. Mars and Jupiter are not just stops. They are the perfect squares on the board, the kind of positions a chess master waits for, and Atlas seems to land on them, one by one. For the public, this is where curiosity spikes. They ask, is it aiming for these planets? Is this a scouting run? Or is it only our imagination dressing up coincidence in the language of strategy? The honest answer is that we don't know. But the game is unfolding in real time, and we are watching from the edge of our seats. Atlas is moving, Mars is behind it, the Sun is its cloak, and Jupiter looms ahead. Every move raises the stakes. Every square crossed deepens the suspense. Orbital chess is no longer a metaphor, it is the game on the board of the solar system. In chess, the knight is often underestimated. Its move looks awkward, an L shape, a sideways jump, but in the hands of a strategist, it becomes the piece that breaks symmetry, that appears where no one expects. Mars plays that role in Atlas's itinerary. Its gravitational influence is modest compared to the giants, but its placement is exquisite. Atlas crosses Mars's orbital lane in early October 2025, the very season when human machines, rovers, orbiters, and satellites are stationed to look outward. On the cosmic board, this is a knight's move. Subtle in force, dramatic in effect. It is not Mars's gravity alone that matters, but the perspective it grants. For weeks, our cameras will align almost perfectly to watch Atlas glide past the red planet's path. The suspense is not whether Atlas will feel Mars's tug, but whether we will witness something unexpected in its glow, its trajectory, or its chemistry as it passes this red square on the board. Then the game accelerates. By late 2025 and into 2026, Atlas arcs outward again, its path curving toward the behemoth Jupiter. If Mars is the knight, Jupiter is the queen, dominant, far-reaching, decisive. Its gravitational sphere of influence is so vast that it has shaped the architecture of our entire solar system, scattering comets, shielding Earth, and orchestrating the outer belts. When Atlas drifts within even the fringes of Jupiter's reach, the suspense multiplies. Will the giant planet pull it inward, altering its direction as though guiding a rook across the file? Or will Atlas skim past, unaffected, slipping through the queen zone like a phantom piece? Either outcome is possible, and both feel strategic. This is why astronomers describe the situation as orbital chess. Each planet is a piece, each encounter is a potential move, and Atlas appears to be advancing in a sequence that matters more than chance. Mars, then the Sun, then Jupiter. The itinerary reads like a playbook. Of course, the cautious scientist insists that these are alignments we notice only in hindsight, coincidences magnified by our imagination. But curiosity refuses to let go, because if this were a human-designed strategy, it would look very much like this: an approach near the smaller planet to test the field, a blackout to maneuver unseen, and then a drift toward the largest player on the board. To put it in everyday terms, imagine watching a car weave through city traffic. First, it slows near a side street where cameras are known to stand. Then it disappears into a tunnel, vanishing from every lens. Minutes later, it re-emerges on the freeway headed toward the largest intersection in town. Is it just a coincidence? Maybe. But from the driver's perspective, it looks suspiciously like a plan. This is the tension of Atlas, whether to treat the sequence as mere geometry or as strategy unfolding in slow motion. The suspense is amplified by timing. Jupiter will not encounter Atlas immediately after the blackout. Months will pass. That gap is itself unnerving. It means that after weeks of enforced blindness behind the Sun, we will have months more of waiting, knowing that the Queen's square lies ahead but not yet reached. It is like watching a chess match where the decisive move is obvious, but the players take long, deliberate pauses before placing the piece. The silence does not calm, it stretches the nerves tighter, and here lies the fascination for both scientists and the public. If Atlas were a random wanderer, it could have cut across the solar system at almost any angle, yet it has chosen by chance, or by fate, a path that brushes Mars, vanishes at perihelion, and arcs toward Jupiter. These are not trivial squares on the board, they are the ones that matter most to us, our neighbor and our guardian. That is why the game feels so intense. It is not just the physics, it is the placement, the sequence, the rhythm of the moves. And Atlas plays them like a grandmaster who knows exactly how long we can hold our breath before demanding the next move. Every chess game builds toward a climax, and in the orbital game of 3 I divided by Atlas. That climax is Jupiter. The red planet was a knight's feint. The Sun served as the momentary shield, but Jupiter is the piece that decides entire battles. With its massive gravity, more than twice the combined mass of all other planets, Jupiter is the queen of the board. To approach it is to step into a gravitational field so dominant that it has shaped comets, redirected asteroids, and even protected Earth for billions of years. For Atlas to drift in this direction is both thrilling and unnerving. Here, the suspense reaches its highest pitch. Will Atlas slip by, its trajectory unchanged, as though mocking the Queen's reach? Or will it be caught in the great planet's invisible hand, bent into a new orbit, flung outward like a pawn captured and hurled across the board? Either outcome tells a story. If it passes unaffected, the coincidence deepens an object that brushes Mars and glances Jupiter, yet moves on untouched. If it shifts course, then the drama intensifies proof that Atlas has interacted with the most powerful piece on the board. In either case, the move matters, and everyone watching knows it. The strategic implications stretch far beyond astronomy. Military planners, when they study orbital mechanics, use Jupiter as a prime example of gravitational leverage, a cosmic slingshot. A spacecraft can steal momentum from a giant planet, redirecting its course across millions of miles. If Atlas were only a comet, its brush with Jupiter would be another chance for nature to show off this slingshot effect. But if Atlas were more, if it carried intent, then the timing looks even more provocative. Mars is the scout square, the Sun is the blackout tunnel, Jupiter is the Queen's file. Each move in sequence, each one amplifying suspicion that we are watching a deliberate itinerary rather than a random path. And yet, clarity requires caution. To label this as design is to cross a line that evidence has not yet justified. The scientific posture remains balanced. Yes, the alignments are striking. but alignments happen in a cosmos of countless possibilities. Suspense is not proof. But curiosity keeps the door open, because if you were to design an orbital reconnaissance, this is exactly how it might look. Use the Sun for concealment, Mars for proximity, and Jupiter for gravity's leverage. Strategy and coincidence are twins here, and only data can decide which one we are truly seeing. For the public, this is where the imagination burns brightest. People picture a ship threading squares on a galactic chessboard, each move too perfect to be random. Scientists picture orbital charts, equations, and gravitational models, each curve a calculation, each possibility waiting to be tested. Between them lies the shared emotion of suspense, the feeling that we are all sitting before a chessboard, watching a master make moves we do not fully understand. The board is vast, the pieces enormous, and the game is played in years rather than minutes. But the tension is the same. Something is unfolding, and we are only spectators. The lesson of orbital chess is not that Atlas is proven to be intentional. The lesson is that strategy can emerge even from chance, that alignments can look deliberate even when they are natural. But it also reminds us that vigilance requires treating these alignments as more than curiosities. They are tests of our ability to stay patient, to remain disciplined, and to prepare for outcomes we cannot yet predict. The suspense is not just in Atlas's moves, it is in ours, how we measure, how we interpret, how we respond when the Queen is finally engaged. As 2026 approaches and Atlas drifts toward Jupiter's influence, the stage is set. The knight has played, the sun has hidden, the Queen awaits. The next move belongs to gravity, but the world will watch as though a hand is guiding it. Orbital chess is more than a metaphor now. It is the lens through which we experience the unfolding mystery. And in this game, suspense is not a distraction, it is the essence. Imagine a suspense film where the villain slips through the city, and at one critical intersection, the hero has a perfect chance to block the escape. The window is narrow seconds, maybe minutes, and if the hero hesitates, the chance is gone forever. That image captures the feeling many astronomers describe when talking about 3I divided by Atlas and the so-called intercept window. For a brief stretch of 2025 and 2026, the geometry of the solar system lines up in such a way that observation, even interception, could have been possible. And yet, reality is harsher than cinema. No mission was ready, no spacecraft dispatched. The window exists, but it will likely remain unused. The centerpiece of this discussion is Juno, NASA's spacecraft orbiting Jupiter since 2016. Juno was never designed as a comet interceptor. Its mission is to study Jupiter's magnetic field, atmosphere, and gravity. Yet by sheer coincidence, it occupies a vantage point that makes it relevant to Atlas's approach toward Jupiter. In principle, Juno's instruments could detect changes in Jupiter's magnetosphere or dust environment if Atlas passes near enough. But in practice, its trajectory, resources, and limited instrumentation constrain what it can do. Juno is like a bystander who happens to be standing on the right street corner when the chase races by. It sees something, but it cannot give pursuit. This is where reality sets in. To truly intercept Atlas, a mission would need to be conceived, launched, and navigated within a time frame of months, a near impossibility in space policy. Building a spacecraft takes years. Funding approval, political buy-in, engineering, launch windows, all these hurdles stretch timelines far beyond what Atlas's trajectory allows. The regret is palpable. We are living in the age of interstellar visitors, but we are not yet living in the age of rapid response missions. The first object, Oumuamua, caught us flat-footed. Borisov gave us a taste of what we might see. Atlas, perhaps the strangest of all, arrives again without our ability to chase. Each missed chance deepens the sense of hesitation, as if we keep watching the same scene where the hero never quite steps into the intersection. And yet, the value of talking about intercept windows is real. It forces the community to acknowledge not just the opportunities, but the gaps in readiness. An intercept is not only about scientific curiosity, it is about demonstrating whether we, as a civilization, are prepared to engage with the unknown. What would it take to have a spacecraft always ready, on standby, to be redirected toward an interstellar visitor within weeks? What resources would it require? What policies would have to change? These questions are not fantasy. They are practical, and the regret scientists feel is that they are being asked only after the windows close. For Atlas, The 2025-2026 window is particularly painful. The object's geometry makes it unusually accessible by Jupiter's domain, and yet no probe will follow. Juno will watch, perhaps glimpse something, but it cannot intercept. Earth's telescopes will record what they can, but the blackout and the distances limit detail. The chance to stand face to face with this anomaly will pass by, and with it comes the lesson. Astonishment at anomalies is not enough. Without readiness, astonishment fades into regret. In policy discussions, scientists often fall back on a useful habit, the checklist. Instead of debating endlessly whether something feels important, they define markers, objective signs that, if triggered, demand action. Applied to 3I divided by Atlas, this approach becomes almost haunting, because the boxes that should light up have already been checked. And yet, no mission is mobilized. That is where the regret sharpens into frustration. We know what to look for, we see it, but we remain spectators. What might such a checklist look like? First, unusual chemistry. Atlas's coma is dominated by carbon dioxide in a ratio of 8:1, an inversion unheard of in solar system comets. Second, improbable geometry. Its near-ecliptic inclination and timed pass near Mars create alignments that look strategic, not random. Third, observational blackout. By vanishing behind the Sun during its critical perihelion, it denies us data at the very moment we most need it. Fourth, looming gravitational interactions. Its arc toward Jupiter in 2026 ensures that one of the most powerful planets in the solar system will become part of the story. Each of these alone would raise eyebrows. Together, they paint a picture that cries out for direct investigation. From a scientific policy standpoint, this is where the concept of an intercept window gains urgency. If you have a checklist of anomalies and a rare chance to catch them up close, you seize it. That is the rational move. Yet in practice, we are constrained by politics and technology. Launching a probe is not like sending a plane. It is like building a city on wheels. Years of planning, billions of dollars, bureaucratic hurdles all collide with the brutal speed of celestial motion. By the time approvals are signed, Atlas will already be past Jupiter, sailing into the dark beyond. Here lies the sting of hesitation. Astronomers admit, with a tone equal parts real and regretful, that we are watching opportunities slip through our fingers. Juno is up there, yes, but Juno is busy, old, and specialized. Its instruments were never tuned for interstellar chemistry. Its orbit is locked around Jupiter, its fuel dwindling. At best, it can provide peripheral data, dust impacts, magnetospheric ripples. At worst, it will contribute little at all. The window is not empty, but it is painfully narrow. We have a spacecraft in place, but not the right spacecraft. We have anomalies to chase, but no chaser. This is where the checklist becomes almost philosophical. What will it take to move from observation to action? How extraordinary must anomalies be before they flip the switch? Imagine if Oumuamua's unexplained acceleration had been paired with Atlas's chemistry. Imagine if Borisov's cometary tail had coincided with a sun blackout. Would that have been enough? Or are we still living in an era where the reflex is always next time? The problem, of course, is that the cosmos does not wait. Each interstellar visitor is a once-in-history event. The next time may come decades from now or tomorrow. The regret is sharpened by the simplicity of the question: how many check marks does it take? For Atlas, the tally is full, and still, the response is to watch, not to act. That restraint is not cowardice, it is realism, born of cost and capability, yet the ache remains. We could be learning so much more if we had the courage, foresight, and infrastructure to launch at short notice. Instead, we settle for telescopes and distant glimpses, letting the object slip through like sand in a clenched fist. And so the checklist hangs in the air like an indictment. The signs were there, the window was open, and we hesitated. Every conversation about Atlas and the intercept window eventually circles back to the same uncomfortable truth. Readiness is not about possibility, it is about will. Technically, we could design a spacecraft capable of fast launch interception. The technology exists in fragments, modular probes, high-thrust rockets, even concepts for nuclear electric propulsion. What we lack is the infrastructure and political appetite to assemble them on standby. Without that, every interstellar visitor becomes another missed opportunity, another chapter where astonishment curdles into regret. This is why the discussion around Juno feels bittersweet. On paper, it is a success story, a spacecraft still alive after nearly a decade in Jupiter's orbit, returning valuable data month after month. But in the context of Atlas, it symbolizes limits. Juno will be there, orbiting the queen of the board as Atlas approaches, yet unable to pivot toward the encounter. Its cameras are designed for cloud belts, not comas. Its instruments are tuned for magnetospheres, not volatile chemistry. At best, Juno becomes an accidental witness, catching a flicker of dust or plasma as Atlas brushes Jupiter's domain. At worst, it will watch nothing at all. We cannot fault the mission. Juno was never meant for this role. The fault lies in our broader lack of readiness, in the fact that we had no other probe to send. And so we look at the intercept window with mixed emotions. The realist in us says, of course, we could not have intercepted. Time was too short, resources too stretched. The dreamer in us says, but imagine if we had. Imagine a probe launched in 2023, arriving in 2025, just in time to sample Atlas's bizarre CO2-rich coma, to image its nucleus up close, to confirm or deny the whispers of strategy in its path. Such a mission would have rewritten textbooks, perhaps even history. Instead, we are left with ground-based telescopes straining through the atmosphere, space-based instruments blinded by the sun, and one aging spacecraft looping Jupiter, not built for the chase. This is not failure, but it is a warning. The universe has given us 3 interstellar visitors in less than a decade. Oumuamua slipped by with no intercept. Borisov confirmed that at least some outsiders resemble our comets. Atlas presents anomalies so profound that they deserve direct scrutiny. And yet, for the 3rd time, we stand on the sidelines. The checklist of action lit up, the window cracked open, and we did not step through. The regret is real, but so is the lesson. That lesson is simple. Astonishment is not enough. Curiosity is not enough. Even knowledge of the intercept window is not enough. If humanity wants to seize these chances, it must build readiness into policy and infrastructure. That means probes waiting in storage, launch vehicles on standby, protocols to greenlight missions in months, not decades. It means treating interstellar visitors not as curiosities, but as tests of our maturity as a scientific civilization. We may not know when the next visitor will arrive, but we know that it will. The question is whether we will be ready, or whether we will once again look back with a sigh and a checklist marked, too late. And so Part 10 closes with a dual emotion. On the one hand, realism. Juno cannot intercept. Our readiness was not there. The window is closing. On the other hand, a quiet ache of regret. This could have been our chance. Atlas will pass, Jupiter will turn the page, and we will be left with only the data we managed from afar. But perhaps, in that mixture of realism and regret, lies the spark of resolve. Perhaps the next time the cosmos sends a wanderer through our neighborhood, the checklist will not end with hesitation. Perhaps the next intercept window will not close in silence. The only time the sun itself blinks is during a total solar eclipse. For a few brief minutes, the overwhelming glare of our star is dimmed by the moon's perfect alignment, and the sky becomes a laboratory. Stars emerge, planets glow, and structures around the sun's corona reveal themselves in ghostly filaments. For astronomers tracking 3i divided by Atlas, this blink is more than a spectacle. It is a rare forensic opportunity, a controlled pause in the blinding flood of photons, when the blackout may briefly be broken, and the interstellar visitor could appear on the edge of detection. The tension is palpable. Under normal circumstances, Atlas is swallowed in sunlight near perihelion, untouchable by ground-based telescopes or even space observatories. The solar glare is too intense, scattering across lenses and drowning detectors in noise. But during an eclipse, nature provides what even billion-dollar coronagraphs struggle to achieve: a window. The moon acts as a cosmic shutter, blocking the solar disk while leaving the surrounding sky momentarily dark. For a few minutes, the impossible becomes possible. The comet hidden by the sun's brilliance could flash into view, like a fugitive illuminated in a sudden sweep of a searchlight. Scientists prepare for this window with military precision. The timeline is unforgiving. Asterisk, before eclipse. Predict Atlas's exact ephemeris, its appointment schedule, on the celestial clock, down to arc seconds. Calibrate instruments, rehearse exposure sequences, and coordinate across observatories on the eclipse path. Asterisk, during eclipse, minutes matter. In totality, cameras fire continuously, coronagraphs record spectra, and every second is treated like gold. The controlled tension is physical breath held, eyes fixed, the world standing still as the sky goes dark. Asterisk. After the eclipse, forensic analysis begins. Photons collected in those fleeting moments are stretched, processed, and compared with predicted orbits. Any deviation, any unexpected brightening, could signal forces at work during the blackout that no one could otherwise see. This is why eclipses feel like cosmic interrogations. The sun hides the answers, but just once in a while, it lets us slip in a question. The hope is not naive, it is cautious, measured, almost reverent. Scientists know the odds. The window may show nothing. Atlas might remain invisible, its glow too faint to pierce the twilight corona, but the chance is irresistible, because the stakes are high. Even a single detection could narrow uncertainties in its orbit, confirm or refute acceleration, or reveal compositional quirks during peak solar stress. The public often sees eclipses as spectacles of wonder, but for Atlas, an eclipse is closer to a courtroom. Nature becomes the judge, and the comet stands at the bar of visibility for a few precious minutes. Suspense builds like a trial where the verdict is hidden in the shadows. Will the object appear? Will it betray secrets? Or will it slip back into silence until November? That is the mix of tension and hope, science holding its breath, disciplined yet eager, knowing that answers may flicker in the blink of the Sunday. During a solar eclipse, tension is not an abstraction, it becomes choreography. Entire teams of scientists treat those few minutes of darkness like a battlefield maneuver. Every instrument is primed, every sequence rehearsed, because there is no second chance. If a shutter jams or a telescope slips out of alignment, the window is gone. That is what makes the experience feel like controlled tension. The anxiety is real, but it is harnessed, disciplined, and transformed into precision. For 3, I divided by Atlas, the stakes are higher than usual. The eclipse is not just about testing theories of solar physics. It is about interrogating an interstellar stranger at the very moment it hides behind the brightest object in the sky. Think of it as orbital forensics. Just as a forensic scientist sifts through traces at a crime scene, astronomers dissect photons gathered during totality. They map each glimmer of light against predictions, comparing what should be there with what actually is. If Atlas appears a few arc-seconds off from its projected position, the displacement hints at hidden forces, a jet of gas, an anomalous acceleration, perhaps even something stranger. If its brightness spikes, the spectrum might reveal compositional fingerprints, CO, 2 bands, dust emissions, thermal signatures no one has seen before. Every discrepancy is a clue, every detection a fragment of testimony in the cosmic courtroom. The timeline of this forensic process underscores the tension. Before the eclipse, models churn with probabilities. Will the moon's shadow fall in the right place to give observers a clear line? Will the weather cooperate? Will Atlas be bright enough? Uncertainty presses down like the weight of a ticking clock. Then, as the eclipse begins, controlled chaos takes over, cameras clicking, coronagraphs tracking, scientists murmuring countdowns. It is not a wonder alone, it is discipline under fire. When totality hits, silence falls in the crowd, but for the teams, adrenaline surges. They know each second is precious, each exposure a lottery ticket in a game with no repeats. Afterward, the mood shifts again. The tension does not vanish, it mutates into anticipation. Hard drives bristle with data, but no one knows yet if Atlas was truly captured. Processing begins, pixels are enhanced, noise stripped away. Often, days or weeks later, a faint streak or spectral line emerges from the darkness. That moment is the controlled release of tension. The discovery is real, but modest, grounded in evidence, not hype. The hope is cautious, because even when data confirms Atlas's presence, it also raises questions. Was its brightness curve consistent with sublimation? Did its trajectory drift more than gravitational models predict? Each answer is provisional, each clue an invitation to dig deeper. This is why eclipses feel paradoxical. They are both fleeting and timeless. Fleeting, because totality never lasts more than a few minutes. Timeless, because the information captured in those minutes can reshape models for years to come. For Atlas, a single frame could alter the debate over its nature. If it glows too brightly, skeptics must admit unusual chemistry. If it shifts in position, dynamics must be rethought. If it vanishes altogether, the mystery only deepens. Either way, the eclipse transforms passive speculation into data-driven dialogue. And woven through it all is that subtle thread of hope, not the exuberant hope of certainty, but the careful hope of investigators. They know disappointment is likely. The comet may remain invisible, hidden behind solar glare, even in darkness. But the hope persists because the window exists at all. It is the universe's rare concession, a momentary dimming of the light, an invitation to look harder. Controlled tension holds the mind steady, cautious hope fuels the effort, and together they create the fragile optimism that maybe, just maybe, Atlas will leave a trace in the blink of the Sunday. When the eclipse ends and daylight floods back, the moment feels almost anticlimactic. The crowd of skywatchers cheers, the spectacle of the corona fades, and the world resumes its rhythm. But for astronomers following 3I divided by Atlas, the real work has only just begun. The forensic phase begins in earnest, sorting through terabytes of images, spectra, and telemetry, all gathered in that fragile interval of shadow. This is where controlled tension evolves into a quiet but enduring pressure. The knowledge that the verdict lies somewhere in the data, waiting to be uncovered. The analysis feels like piecing together a crime scene. Investigators examine every angle, every frame, every unexpected pixel. Did Atlas appear precisely where the models said it would? If yes, the relief is temporary. Predictability means normal forces still dominate. If not, the deviation itself becomes evidence. Perhaps an outgassing jet, perhaps a non-gravitational push. Did its brightness match sublimation models? If brighter, the chemistry may be stranger than we imagined. If dimmer, it may be cloaked in dust or exhausted of volatiles. Each possibility is a branch in the forensic tree, each requiring patience to pursue. What makes the solar eclipse window unique is that it carries weight beyond one event. These few minutes can anchor years of speculation. If Atlas reveals itself, even faintly, its trajectory can be locked down with unprecedented precision. That changes not just where it is, but where it will be shaping the story of its approach to Jupiter in 2026. If no trace is found, the absence itself becomes testimony. The silence would speak loudly, suggesting either extraordinary faintness or behavior we cannot yet model. In forensics, absence of evidence is never simply nothing. It is another kind of clue. This is where cautious hope softens the tension. Scientists know that discoveries often come not as dramatic revelations but as small, stubborn details. A faint streak on a processed image, a spectral line just above the noise, a deviation of a fraction of an arcsecond. These are not headlines, but they are the building blocks of truth. Hope lies not in expecting fireworks, but in trusting the discipline of evidence. Even if Atlas remains elusive, the act of using the eclipse as a window cements humanity's commitment to not waste the opportunities the cosmos offers. For the public, the narrative becomes almost cinematic. The sun blinked, and in that blink, we tried to catch a trespasser in the act. Maybe we glimpsed it, maybe we didn't. The tension was real, the hope restrained, the outcome still unfolding in laboratories long after the shadow moved on. This is science in its rawest form, not certainty, but pursuit, not final answers, but careful steps in the dark. The eclipse window reminds us that knowledge often advances not in leaps, but in cautious increments, in moments where the cosmos grants us just enough silence to ask one more question. And so, Part 11 closes with a verdict that is not final, but provisional. The eclipse gave us a chance. Whether that chance bore fruit depends on analysis yet to come. But the value is already clear. The act of readiness, the embrace of controlled tension, and the persistence of cautious hope. Atlas has once again forced us to confront the fragility of our tools and the resilience of our curiosity. The sun blinked, and for a moment we stared into its shadow, searching for truth. Whatever the results, that search itself is the heartbeat of science. When the comet disappears, science does not panic, it investigates, like detectives arriving at an empty house where the footprints remain. The weeks when 3I divided by Atlas vanished behind the sun felt like a blackout in surveillance footage. The subject walked off screen, the cameras went blind, and the mystery deepened. But the investigation did not stop. Instead, it shifted into the quiet, rational phase of hidden surveillance and after-gap forensics, where patient evidence gathering replaces spectacle, and progress is measured not in dazzling discoveries, but in careful reconstruction. Space surveillance is not one telescope or one country, it is a patchwork of sensors, orbiting Earth, stationed on satellites, mounted on ground radars, and sometimes classified within military networks. These systems were not built for comets. Their first duty is to track debris, satellites, and potential threats to navigation. But like detectives stumbling on unexpected clues while checking routine patrols, they sometimes catch glimpses of phenomena far stranger. During Atlas's blackout, fragments of infrared signatures, streaks in wide-field images, and anomalies in orbital catalogues began to accumulate quietly, almost unnoticed outside expert circles. Each fragment was tiny, but together they formed the raw material of after-gap reconstruction. The analogy to forensic science is deliberate. When investigators arrive at a crime scene after the fact, they cannot see the event itself. Instead, they sift through what remains: footprints in dust, fingerprints on glass, fibers caught in fabric. In the case of Atlas, the fibers are photons scattered on detector arrays, the footprints are small deviations in star tracking images, and the fingerprints are heat signatures barely above noise. Alone, none are definitive. But with patience, they become evidence. Piece by piece, the missing weeks can be sketched back into a story. What makes this phase striking is its emotional texture. The blackout had been dramatic, a moment of suspense and helplessness. The return to data analysis feels calmer, steadier, almost stoic. The thrill is not in seeing Atlas blaze across the sky, but in knowing that careful logic can retrieve what spectacle concealed. This is rational science at its core. Not dazzled by absence, not defeated by uncertainty, but moving forward step by step, sifting noise from signal, chasing truth in the margins. For the public, this phase can feel slow, even anticlimactic. There are no breathtaking images, no viral headlines. Instead, there are spreadsheets of star positions, long chains of calibration logs, and stacks of Fourier transforms. But hidden inside these dry rituals is the patient heartbeat of discovery. The payoff does not come in a flash. It comes weeks or months later, when patterns emerge, when the ghost of Atlas reappears in reconstructed orbital charts, when the forensics close the gap left by the blackout. And that is why controlled patience is not a weakness here, it is the very strength. Just as detectives trust that even the faintest clue can solve a case if handled properly, astronomers trust that the comet's secrets did not vanish behind the Sunday. They are still here, encoded in faint traces, waiting to be decoded. The work is slow, rational, and disciplined, but it is also deeply human, a refusal to let the trail go cold, a belief that persistence can wrestle meaning from silence. If the first phase of after-gap forensics is about recognizing the clues, the second is about weaving them into a narrative. Imagine investigators spread across continents, each holding a fragment of surveillance footage from a missing person. One has a blurry outline from a street corner camera. Another has a timestamp from a toll booth. A third has audio from a passing phone call. None mean much alone, but stitched together, they become a timeline. This is exactly what happens when astronomers and space agencies pool their resources after Atlas's blackout. The raw ingredients come from everywhere. The US Space Surveillance Network, designed to track orbital debris, occasionally picks up faint objects that wander near its fields of view. The European Space Agency's Space Situational Awareness Program catches streaks across wide-angle frames. Infrared telescopes in orbit record slight temperature anomalies, so faint they look like noise, until reanalyzed with Atlas's trajectory in mind. Even ground-based amateur networks, high-speed cameras meant to record meteors, contribute streaks that only later are recognized as fragments of the comet's tail. Each of these is a sliver of evidence. Each requires patience, context, and rational interpretation. What follows is an investigative process that feels eerily like law enforcement. Analysts timestamp every detection, correct for instrumental drift, and cross-check against catalogued satellites and known asteroids. Noise is stripped away. False positives are eliminated. Slowly, what looked like random clutter in different archives begins to align. The same faint signature shows up in multiple datasets, at different times, in the right places. With each confirmation, confidence grows. Atlas has been found again, not in blazing visibility, but in the hidden surveillance logs of our spacefaring infrastructure. This phase is less dramatic, but more powerful than the initial spectacle. It shows that the cosmos cannot truly hide from a civilization that has spread its sensors everywhere. Even when Atlas vanished behind the sun, its influence lingered, light bent, dust scattered, faint infrared warmth left a trail. The rational scientist's role is to follow that trail with calm precision, resisting the urge to leap to conclusions, letting the evidence dictate the narrative. It is slow work, but it transforms absence into presence, mystery into measurement. The emotional tone here is different too. During the blackout itself, the feeling was helplessness. A wall of light we could not see through. In this after-gap forensic stage, the mood becomes patient confidence. The truth will come, not in a flash, but in incremental gains. Each new detection strengthens the model of Atlas's path. Each refined trajectory narrows uncertainties. By the time weeks or months pass, astronomers can reconstruct with astonishing precision where the object was, how fast it moved, and whether it deviated from pure gravitational prediction. For the public, this part of the story may seem less cinematic but more reassuring. It demonstrates the resilience of science. Even when blinded, even when caught off guard, the network of observation adapts. The comet may hide, but footprints remain. And those footprints, tracked by rational patience, tell us almost as much as direct sightings. The metaphor of forensics is apt. We rarely catch the event itself on camera, but the evidence left behind testifies clearly if we know how to read it. This is why space surveillance and forensic reconstruction represent not just technical skill but a philosophy. It embodies the belief that the universe cannot erase its traces, that patient inquiry always finds a way to close the gaps. Atlas challenged us by disappearing. Our response is not despair, but persistence. And that persistence, steady and logical, is what keeps the search alive long after the spectacle has faded. By the time the after-gap reconstruction reaches completion, the sense of urgency has given way to something subtler but no less profound. Rational patience rewarded. Atlas re-emerges not as a dazzling streak across the sky, but as a carefully plotted curve on orbital charts. Each data point the product of weeks of painstaking work. For outsiders, this may feel anticlimactic, but for those invested in the process, it is deeply satisfying. The comet story is written again not because it chose to reveal itself, but because our methods refuse to let it vanish. This is where the philosophy of forensic science in astronomy comes into its clearest light. Just as a detective does not expect a confession from the suspect but instead reconstructs the truth from fingerprints, fibers, and timelines, astronomers do not expect Atlas to explain itself. Instead, they let the evidence speak. Every anomaly is weighed against models. Every spectral oddity is compared to baselines. Every orbital deviation is checked against gravitational theory. The result is not a dramatic revelation, but a coherent narrative stitched from fragments. Rationality provides the framework. Patience provides the endurance. The lesson for both scientists and the public is that discovery is often less about fireworks and more about persistence. The blackout was dramatic, the sun blinding our eyes, the comet slipping from view. But the real victory lies in the aftermath, when quiet teams sifted through noise until order emerged. The tension of the eclipse has been replaced by the calm of evidence. The mystery has not been solved in full, but the gap has been bridged, and that bridging is itself an act of triumph. Yet the emotional undertone here is not triumphalism, it is humility. The reconstruction reminds us how fragile our vision still is. We rely on fragments, on accidental detections, on networks designed for other purposes. We succeed because we are thorough, not because we are omniscient. That humility carries value. It tempers speculation, grounds hope in evidence, and reminds us that patience is not optional but essential. Without it, we would mistake coincidence for cause, noise for signal. With it, we build knowledge brick by brick, no matter how slow the process. For the public, this stage may seem quieter, but it contains its own drama. It is the drama of waiting for lab results, of following an investigation day after day, knowing the answer will not arrive in a single flash but in steady accumulation. Controlled rationality is the mood, but beneath it runs a current of faith. Faith that science, however plodding, will illuminate the dark. The hope here is not reckless, it is measured hope, the kind born from method rather than wishful thinking. So Part 12 closes not with spectacle, but with resolve. Atlas slipped behind the sun and tried to vanish. But the traces remained, and rational patience retrieved them. We now know where it was, how it moved, and what faint evidence it left in its wake. The blackout has ended, not in despair but in reconstruction, and that reconstruction carries a larger lesson. In a universe where anomalies will come and go, it is not brilliance alone but persistence, patient, rational, forensic, that ensures the truth will not be lost.